Dear guests, please gather in the main room. Our program is about to begin. الرجاء التفضل بالجلوس، سنبدأ بعد دقائق. الرجاء التفضل بالجلوس، سنبدأ بعد دقائق. Dear guests, please gather in the main room. The program is about to begin. الرجاء التفضل بالجلوس، سنبدأ بعد دقائق.
the depths of the earth, the light of progress comes. In the accelerating world of technology, semiconductors play a pivotal role in developing the innovations that shape our future. Silicon raw material is formed from sand to become the beginning of the manufacture of electronic circuits. This stage lays the basis for transforming a raw material into advanced products. Design experts are working to find technical solutions that enable us to harness the power of semiconductors. The raw silicon material is transformed with the skill and experience of workers in the clean room laboratory into precise electronic circuits that form the heart of the new technology. Electronic circuits made of semiconductors represent the cornerstone of various vital sectors, starting from human health and environmental sustainability, passing through leadership in energy and industry, and ending with the economies of the future. The Kingdom is striving to create an ecosystem for localizing semiconductors by providing an ideal environment for research and development, supporting entrepreneurs and startups. These national efforts aim to transform the Kingdom into a global hub for the semiconductor industry.
Your Excellencies, the Ministers, our distinguished audience of creators, innovators, and aspirants, our dear guests from within and outside of the Kingdom. I am Sohan Welati, and I'm honored to be here with you today. And we greet you all from here, from Riyadh, the city of innovation and the sponsor of science and technology. Welcome everyone to the third edition of the Future Semiconductors Forum, held under the theme Empowering Silicon Innovations in King Abdulaziz City for Science and Technology in Riyadh, and in partnership with King Abdullah University of Science and Technology. We are here today to celebrate creativity and innovation within an ambitious vision that carries the torch of prosperity of the region and the world as a whole. I would like to extend a special welcome to our esteemed guests, including ministers, officials, decision makers, and experts who have joined us today. We are grateful to you for dedicating your time to participate in the third edition of this forum, and we look forward to your fruitful contributions in the discussions and sessions. Today, we are gathered here to learn, share, and collaborate. This platform provides us with a chance to exchange ideas and knowledge about the newest technologies in the semiconductors field. I hope you all have a fulfilling learning and interactive experience, and thank you all for attending, and we look forward to an inspiring day. And now, I am honored to welcome on stage Dr. Saeed al-Shehri to deliver his speech.
السلام عليكم. Distinguished guests, ladies and gentlemen, good morning and thank you for joining us today. It's my pleasure to welcome you to the third edition of the Future of Semiconductors Forum, organized by KACST and KAUST. This forum has grown to become the leading event for the semiconductors in the Kingdom and the region. Today, we aim to shed light on the efforts and advancements in this vital sector. And we are proud to provide a platform for discussing the transformative changes and the innovative developments that shape the future of semiconductors. At King Abdulaziz City for Science and Technology, we are committed to fostering research, development, innovation, and collaboration in this critical area. And we believe through partnership, knowledge exchange, and also the investments in this critical area will unlock new opportunities to address the challenges of the future. Throughout 8 insightful sessions, we will be delighted to listen from more than 40 experts who will share their knowledge and expertise in different areas of semiconductors. We also extend our gratitude to our sponsors whose support highlights the significance of this forum. And your belief in this, the importance of this gathering, is truly appreciated. Today's forum is a testament to our vision and dedication, and I'm confident that insights, discussions, and collaboration that will come from this event will lead us toward a brighter and more technologically advanced future. Thank you again for joining us, and I wish you all a fruitful and productive forum. Thank you very much.
Thank you very much, Dr. Saeed. And now, please welcome on stage the President of King Abdullah University for Science and Technology, Dr. Tony Chan.
Assalamu alaikum. Good morning, everyone. I'm trying to recognize all the excellencies. I see His Excellency Alet, our father is there. His Excellency Abdullah Al-Swaha is there. It's difficult for me to see everyone. But anyway, welcome and thank you for this great partnership between KACST and KAUST and all the ministries. Let me end my welcome to others that I've given you for this is the third Future of Semiconductor Forum, partly organized by KAUST and KACST. Let me also thank Dr. Altisuki. Is Munir there? Yeah, so he should be. Okay. And KACST, of course, for hosting all of us here today on the KACST campus. I still remember 6 months ago, we had this forum at KAUST. His Excellency Hala Al-Fala was a keynote speaker, I remember. We all remember that very well. I'm also honored to have this opportunity to speak to you this morning and share my thoughts on the importance of the semiconductor ecosystem, R&D, and industry for Saudi Arabia and also Vision 2030. As I said last year, KAUST hosted this forum and 850 people attended the event. This year, it seems that the number are even larger. This forum brings together experts and stakeholders from academia, industry, and government to discuss critical topics that will shape the future of the semiconductor industry. Semiconductor has become one of the hottest topics these days, not only in the technology circles, but also in economic, geopolitical circles, as well as in the media coverage. Hardly a day goes by without some headline news about it globally. Once esoteric terms such as GPUs, NVIDIA, TSMC, SMIC, ASML have now entered the public lexicon, and the trend is accelerating. I expect nothing less from this forum than for it to further advance semiconductor research in the kingdom and also globally, and for the next few decades. We have a fantastic lineup of high-level speakers, including Minister of Communication and Information Technology, His Excellency Al-Swaha, also His Excellency the Minister of Investment, Alet I just mentioned, and also KACST President, Dr. Munir Al-Dasuki, and also, I just said hello to Nobel Prize winner, Suji Nakamura, all the way from UC Santa Barbara, and all-star cast of speakers and experts in the audience. Now, the forum includes sessions that cover the most pressing topics on the future of semiconductors, including opportunities in the semiconductor landscape in the kingdom, growing pockets of semiconductor excellence in the kingdom, aerospace electronics, 6G communication, and beyond, photonics, semiconductor packaging, Internet of Things, and electrical vehicles. These sessions offer an excellent opportunity to learn about the latest advancement challenges and also opportunity in the semiconductor industry. I would also like to acknowledge and express our gratitude to the generous sponsor of this event, including Ajlan Brothers, Trist Tech, Oxford Instruments, NISAC, Silvaco, and many, many others. We appreciate your generous support and your commitment to driving innovation and growth in the semiconductor industry, especially in the kingdom. At KAUST, we are committed to developing world-class research and innovation capabilities in the semiconductor sector. We have made significant investment in the last few years to establish a state-of-the-art semiconductor research and development facility that supports our mission to be a leading contributor to the national effort. We started the KAUST Semiconductor Initiative, bringing together more than 30 faculty members and hundreds of students and researchers to work on a range of critical R&D topics for Vision 2030. Our team of experts is working on advanced materials, devices, and systems that will enable new applications and pave the way for the future of the semiconductor industry. We have research partnerships with a number of local entities such as NEOM, KACST, NTIS, just to name a few. We have also started a dialogue for partnership with Alet. I understand the CEO will be speaking later this morning. In terms of training and research, we are committed to doubling down the investment in these areas together in our partners in the kingdom. We have also started a special one-year diploma program on integrated circuit design, which will provide trained manpower in the kingdom for the fabless models. In conclusion, this forum is a testament to the Saudi Arabia's commitment to the semiconductor industry and the potential it holds for the future. It is a collective effort led by KAUST and KACST, and in particular in partnership with many Saudi university organizations and companies. We must continue to invest in this industry and work together to create a brighter future for Saudi Arabia. Now, I would like to add a personal note before closing. When I was still active in research, I worked in the semiconductor area, specifically in semiconductor device simulation, in partnership with Bell Labs and IBM, as well as an EDA, electronic design automation, with a collaborator from UCLA. I know, for example, that doping, in this field is not about drugs. And I witnessed the exponential increase in number of cells that are packed into a wafer, challenging existing physical design methodology and algorithms. That experience, personal experience, has given me a heightened appreciation of the creativity and an innovation that has gone into this field's advancement over the last few decades. So thank you very much. I wish you all a very successful and fruitful conference. Shukran.
Thank you very much, Dr. Tony. And it's time to learn now the details of the forum from the people in charge. I would kindly ask to invite His Excellency Dr. Munir bin Mahmoud Al-Dsuki, President of the King Abdulaziz City for Science and Technology, to deliver his speech.
Your Excellencies, ladies and gentlemen, good morning for the third time, since this is the third forum for semiconductors. A topic that outside of this room was not known to many until this happened in 2019, where we've all faced shortages in supply chains and disruptions that had led to many countries putting strategies for semiconductors. There was a big debate: would these shortages last? Will they change over time? Will there be actually an oversupply? Something that now is apparent in the media. But one thing was for certain: there will always be a shortage of talent, and talent in this area is very scarce. So in King Abdulaziz City for Science and Technology, we had leveraged a semiconductor clean room that was launched in 2021, a state-of-the-art facility that covers 1,600 square meters, but more importantly, that is equipped with almost 50 talented Saudis that work on the whole supply chain from back end to front end, from the design to the manufacturing. And we're very proud of the talent that we have in this lab. But obviously, we can do a lot more with what we have here. So with the announcements from His Royal Highness, Crown Prince and Prime Minister, Prince Mohammed bin Salman, on June 30th of 2022, of the national aspirations and priorities of the kingdom for research, development, and innovation, there were 4 priority areas that were set: health and wellness, environment and sustainable supply of essential needs, energy and industrial leadership, and last but not least, economies of the future, of which semiconductors belongs to. And in the first forum that was held here in KACST in 2022, we had the honor of launching the Saudi Semiconductor Program, a program that aims to provide multi-project wafer services to a network of local universities. We've reached 18 universities as part of this network today. With these services, we're not only providing access to our clean rooms at KACST, but also access to cutting-edge foundries from around the world through multi-project shared wafer services that really bring down the cost for researchers and students to access such technologies. But we've also focused on the talent development side. And over the past year and a half, we've managed to train over 500 Saudis throughout the program. I'm proud to say that many of them actually have been hired through the companies that operate in the kingdom, that operate clean rooms and other facilities. They've taken the graduates of this program and hired them. Some of these students have shared their stories. They used to be graduates of chemistry or physics that were engaged in teaching, a very honorable profession. But once this opportunity came up, they came to our clean room, they trained into a new domain and got a job in manufacturing semiconductor components. But we didn't focus only on experienced people and reskilling. We went all the way down to high school students. And we were very proud with the high school students from Mawhiba program, very gifted talent that trained in our clean room over the past 2 years and went to compete in global competitions with winning a number of awards. And we're going to hear from 2 of these students today on stage during our opening ceremony. Their talk, I guarantee you, is going to be much more exciting than mine. And then we've launched the garage, where we're meeting and sitting here today. A parking building that used to fit 480 cars, converted into a space for deep tech companies that can fit and host up to 300 companies. But the true advantage of the garage was that it was located within walking distance from our national labs, with access based on an open access policy that was approved by the Council of Ministers to all publicly funded research infrastructure, to all of our labs. So every company hosted or incubated in the garage can access all of the labs that we have at KACST, including our Saudi Semiconductor clean room. So we've seen 5 semiconductor companies come and sit in the garage, a number of them moving here from the Silicon Valley. So we launched a dedicated incubator and accelerator focused on semiconductors called Ignition that targets hosting companies for up to 1 year to access our clean room and accelerate bringing this to market. And I'm very proud today that I see my PhD supervisor sitting there, Professor Jamal Deen, who I met 20 years ago, who flew in here from Canada to move his startup to the garage and just registered it yesterday. The garage hosts today companies from over 50 countries from around the world. So we want to take this effort even further in collaboration with the local partners, with our network, to really enhance the talent development in the semiconductor domain. So we're proud today to announce that we're pushing our partnership with KAUST even further with the launch of a national capability center that will combine both of our clean rooms for a total area of 3,600 square meters, accessible to over 30 universities through a joint portal, with the target of training 500 engineers per year. And for the first time in the kingdom, there's the announcement of launching a joint semiconductor master's degree between Princess Noura University and UCLA as a joint degree. And we're honored to host more than 35% of the activities of the master's students in our clean room at KACST. The target is to admit 20 students during the first year. But to pull all of this together and to capture the efforts of the talents that we're training and the incubator that we're doing and the companies that are rising, I have a very exciting announcement that will be shared by the Research Development and Innovation Authority by my colleague, Dr. Mohammed Al-Ataibi. So I'd like to invite him to the stage. Thank you, everyone.
Good morning. Thank you very much, Your Excellency. Welcome, everybody. It's really great to be here. So, as Dr. Mani just mentioned, the semiconductor is actually in the heart of all this global change. It's the brain cells that actually drive and allow the artificial intelligence to process and store data. And it's projected to be more than $1 trillion US dollars industry over the next few years. So Saudi Arabia must actually play a role within this industry globally and regionally over the coming years. So we are here at Research, Development and Innovation Authority. We are playing a pivotal role for the kingdom's development of semiconductors. We are strategically positioned in order to align all the national institutions that's actually doing or developing semiconductor and conducting research, whether that's NEOM, Alet, KFUPM, and of course, KAUST and KACST who are organizing this event. So RDIA is aligning our semiconductor under one national umbrella to support local semiconductor, hopefully a growth of a local semiconductor industry over this coming few years. So we in RDIA will do this by being a strategic alignment enabler, connecting the ecosystem stakeholders. We'll do so also by being an industry attraction epicenter, piloting programs to attract international semiconductor industry, and also to be a semiconductor technology promotion hub. To support the kingdom's ambitions, today we are announcing a national semiconductor hub. So this initiative will establish a fabulous design hub that will help the kingdom to build the required knowledge for this industry. It also will promote the Saudi Arabia as an attractive relocation country for international semiconductor design companies, as well as creating a high quality jobs in the kingdom. If you allow me, Your Excellencies, I would like to invite my colleagues, who is the mastermind behind this initiative, Dr. Naveed Sharwani, to join me on the stage. So here he is, so to say a few words about this.
Thank you, Dr. Mohammed. Your Excellencies, it's great to be here on this and you joining us for this great day for the kingdom. What we plan to do is we want to build a semiconductor industry, fabulous chip design companies in the kingdom. And how do we plan to do that? I think our goal is very simple. We will focus on an ecosystem of fabulous design companies. These are the companies which design the chips, but they will be manufactured with various different semiconductor fabs in the world. We plan to create a value of 50 billion Saudi riyals in 5 to 6 years as part of the Saudi Vision 2030. How can we do that? How is even that possible? Step 1, we resolve to establish 50 fabulous semiconductor companies here in 5 to 6 years. You might say, how many companies are here? How is it possible that we can have 50 companies here in 5 to 6 years? Let me tell you the good news. We already have 3 companies signed up, while our goal this year was to have 5 companies. 3 companies are already here, and 10 companies have asked us to join. So the question is, how do we get the other 47 companies in the next 6 years? We plan to do 4 things. Number 1, we want to create world-class incentives. We want to make this place feel like Silicon Valley. How do you make it feel like Silicon Valley? You make it feel like Silicon Valley because we free space. We provide them all kind of incentives for salary, for relocation. In total, there are 10 incentives we will provide to anybody who wants to start a company here in collaboration with National Technology Development Program. In addition, we will all created a company called Epic Semi, which will provide you all services that you need. This company is already established. It will provide you wafers, packages, multi-part wafers, IPs, anything that you need to start the company, it will be here. The company is already here. The second thing we will do, what is the biggest problem that companies have? Funding. What we plan to do is to create a fund along with a consortium of all the investors in the kingdom. We are starting with 1 billion Saudi riyal. This concentrated effort will allow us to make sure that our founders are not investing their time raising the money and spending the time in doing what they do best, building the companies. So today we are announcing a 1 billion Saudi riyal to help fund these 50 companies. Then the last question you may ask me, okay, you have incentives, you can get the companies here, you have funding, where are the people? Who is going to work in these companies? So we are launching a plan to attract 25 world-class experts, semiconductor experts, to come here, give us the vision, advise our companies, and make sure that they need whatever support they need to become world-class companies. I can tell you the good news, 2 of the experts are already here. We have 23 more to hire. Lastly, where are the engineers? In order to launch this program successfully, we would need around 5,000 engineers over the next 5-6 years. We plan to hire, relocate, and train these people, not just in Riyadh, but all the other promising locations inside of the kingdom and in the neighboring countries. We have already launched 2 training programs, one here in the kingdom and one in the neighboring country. And inshallah, our goal is to hire 500 engineers in the next 12 months, and we already have a clear line of sight to hire those 500, inshallah, in the next 12 months. Last thing, before I end, if I have to thank one person for making sure this program is here. It is His Excellency Abdullah Swaha. From the first day, I met him to this day. It is his personal interest, personal intervention on every aspect of this program to make it happen. Thank you, sir. Thank you very much.
The impact of innovative chip design reaches far beyond individual devices, driving advancements in artificial intelligence, healthcare, transportation, communication, and numerous other fields. In its mission to establish a semiconductor ecosystem in the kingdom, KACST has constructed a 1,600 square meter class 100 clean room, accessible to local researchers, entrepreneurs, and the private sector. In 2022, KACST has launched the Saudi Semiconductor program to leverage its highly educated researchers and state-of-the-art clean room. KAUST has also established a world-class semiconductor RDIA ecosystem, including hundreds of leading Saudi and international scientists, engineers, and technicians. Thousands of KAUST alumni are active in the semiconductor industry all over the world. In addition, KAUST Nanofabrication Core Lab, NCL, consists of world-class lab space, including 2,000 square meters of clean room facilities for advanced materials, devices, and integrated circuits. Today, to further national efforts to build the semiconductor ecosystem and achieve the goals of the Saudi Vision 2030, KACST and its partners proudly announced the 3 new initiatives to enhance the local semiconductor ecosystem capabilities, talent pipeline, and IC design industry. First, KACST and KAUST are combining their expertise and resources once again to foster innovation and knowledge exchange through the launch of the National Capability Center of Semiconductors, NCCS. This joint center provides access to 3,600 square meter of combined semiconductor facilities for 30 Saudi universities. Next, KACST is collaborating with Princess Noura bint Abdurrahman University and UCLA to launch a master's degree program in semiconductors, aiming to admit 20 students annually. This program focuses on human talent development, with 35% of training time conducted in KACST clean room. Finally, Research Development and Innovation Authority announces the launch of the National Semiconductor Hub, aimed at fostering the IC design industry inside Arabia. This initiative plans to attract 50 IC design companies to the kingdom and train over 5,000 IC design engineers by 2030, creating high-quality jobs and advancing the local semiconductor industry, and achieve more than 150 million Saudi riyals in various support products provided by the National Information Technology Development Program, in addition to attract over 1 billion Saudi riyals in venture capital and deep tech investment funds by 2030. Also to attract international experts and specialists through the Saudi Premium Residency.
Your Excellencies, ladies and gentlemen, before we conclude, and for this beautiful celebration to be complete, now let's welcome on stage the 2 talented students who have demonstrated their talent in research, development, and innovation to share their unique stories. Please welcome Sarah Shiddi and Fajr Al-Khlefi.
Assalamu alaikum. Can you hear me? Assalamu alaikum. My name is Sarah Shiddi. I'm currently a senior in high school who's about to graduate, and I'm about to start college at UPenn Wharton this fall. I'm someone who has many different types of interests, and I like to explore those interests to see what I really like. So last summer, I participated in a research program held here at KACST, sponsored by Mohiba. And when I was there, I was thinking about issues that are widespread around the world that everyone or a lot of people face. One of them is water scarcity. And I thought back to my origins. I come from a region here in Riyadh called Hremla. It's a place known for being dry, remote, and one of the main sources of water comes from wells. But in other sides of the world, where well water is the main source, well water is contaminated with bacteria, and not every place has places that decontaminate water in an affordable or sustainable manner. So what I did is that I proposed the development of a UV LED water treatment system that uses Arduino to control the system and different sensors using semiconductor materials. So when I created the prototype in the summer, I realized that, okay, I'm using commercialized sensors, commercialized materials. It was efficient, but I couldn't upscale it or kind of commercialize it. And so that's when I went to the KACST clean room. There, I chose many different semiconductor materials and kind of compared them to see which one was most efficient, most cheap, most reliable. And that's when I chose gallium arsenide as the perfect semiconductor. And when I created the sensor, the light sensor that detects the light that the UV LED kills the bacteria, I found that it's 70% cheaper and much more reliable than what's already available in the market. So naturally, I was really, really excited with my project. And I signed up for Saudi Arabia's National Olympiad for Scientific Creativity called IBDAع. And this competition has 4 stages of judging, which start from regionals and end to finals here in Riyadh. So when I went to finals, I saw different students who were very, very passionate about their projects. It was inspiring seeing people my age who have such niche interests and they want to solve problems that hit close to home like me. So at the award ceremony in IBDAع, I couldn't believe my ears when I heard my name being called out for the special award for Aramco. And when I got the award, I was really excited, and then I got a phone call saying that award raised my candidacy to be a part of the Saudi national team for the Geneva International Exhibition for Inventions. So naturally, I was so excited, but I didn't know what to expect. It was nerve-wracking representing my country in such a big competition. And when I first got there, I noticed something that I did not think was going to happen. I was used to competitions for high schoolers like IBDAع or ISAF, but in the Geneva competition, there was no age limit. I saw people with PhDs, people with masters. I saw projects with multiple credentials, and I didn't even start college. So I was a bit nervous. I thought my project was too simple, it wasn't too competitive. And when I saw the prototypes, I saw people with huge, huge prototypes. I even saw something as big as a tanning bed. But the only thing I got was my sensor. And it wasn't even this big. Imagine this, but 40 times smaller. That was my sensor. So I showed the judge my tiny, tiny prototype. And I told him, it's tiny, but it's reliable. It's exactly what I wanted. And that's the beauty of semiconductors. Although they're small, they're not grand, they're not huge, they're efficient, and they're very, very reliable. So he was impressed. And at the award ceremony at the Geneva project, invention competition, I won the highest level award available, which is a gold medal with distinction. Along with a special award from Hong Kong Polytechnic University. And it was exhilarating, honestly. To represent my country and come back home with a gold medal, it was something I couldn't even describe. It felt so nice, and I was happy that the judges could see the potential of my project. And when I was there, actually, I saw investors who were looking into projects that were like prototypes that didn't commercialize yet or upscale. And that's actually why I want to study at Wharton, study economics. You might be like, you have the scientific background, you worked in labs, why would you want to study economics? I saw this lack in economists, in scientific fields. I saw so many scientists. I'm surrounded by so many scientists, but I saw this gap, and I'd like to bridge that gap by studying at Wharton this fall in college. And lastly, I'd love to thank KACST for providing me with all of these resources, and I'd love to thank His Royal Highness, Crown Prince Mohammed bin Salman, for supporting these things and supporting these initiatives. Yeah, thank you so much for listening.
Assalamu alaikum. I'm Fajr Abdelmajid Lakhlefi, a mechanical engineering student in my first year at KFUPM. 2 years ago, I joined a research program here at KACST that was proposed by the Mawhiba Institution. You may wonder why I chose this particular research program. So let me tell you. Among us students, KACST is well known for its scientific resources and its strength in various fields. So from all the fields that KACST offered, I chose to venture into the fields of material sciences and energy. I proposed an idea of generating energy from an unusual natural resource, which is raindrops. The idea came to me after I witnessed the beginning of the cloud seeding program. And one of the great results of this program is that it produced more than 4 billion cubic meters in 2023. And also, we have some drawbacks in solar panels, such as that they don't work if there is no sunlight, and they have efficiency drops when the sun is at its peak times. So I went with raindrops. At the beginning, I have so many doubts about my project, and I thought that it was impossible to do due to many challenges. However, after my initial exposure to the world of semiconductors, my project became feasible. I started by designing microstructural electrodes, and I conducted some simulations using COMSIL simulation software. And then I thought that what will really help me to bring my idea to be a working device? And the answer was KACST Clean Room. This well-equipped clean room, which is crucial for semiconductor manufacturing, was the perfect environment to turn my theoretical concept into practical innovations. I trained in them and expanded my knowledge more about them, and worked for over a year on my project. At the end, I fabricated a device, and then I integrated it with solar panels to develop an efficient hybrid system. One of the results that I got from my hybrid system is that it produced 0.8 volts per 1 raindrop. This number may sound a little bit, but in real life, we're talking about millions of raindrops. So eventually, my hybrid system had the ability to efficiently transform any mechanical stress into electrical energy while also exploiting sunlight and heat. I've never imagined to go in this experience and work with such delicate technologies like semiconductors. And in my opinion, semiconductors can manufacture things that make life easier and drive progress. At the last year of my high school and before entering college, I was nominated to the national competition IBDAع. And from there, I participated in the largest international competition for research, ISEF. Recovering my journey and the countless hours I spent in the labs between failed devices and many experiments, alhamdulillah, among thousands of students, I won a top award in ISEF. This was a proud achievement to me, and it showcased the potential of young Saudi innovators in cutting-edge technology. And winning this prize motivated me to keep working on new ideas and achievement. So from there, I filed for a patent and submitted an article on microstructural designs to generate energy using piezoelectric materials. My experience can be concluded in one device, which is this. This is the device that I've worked for over 2 years to achieve at the end. And my experience in the world of semiconductors and microfabrications helped me and guided me to choose my university major in mechanical engineering. This decision was really fueled by my passion for new adventures in the world of technology. And now in university, I'm still working in semiconductors and similar projects, building on what I've learned from KACST. And since day one of this journey, I've always hoped to become like one of the great scientists I've worked with and to continue contributing to the world of semiconductors here at KACST. And in conclusion, I want to extend my gratitude to His Excellency Abdullah Suwaha and His Excellency Munir Tsugi for their numerous opportunities that they provide to us young Saudi innovators and for their unwavering support. My journey began 2 years ago. However, it continues today with many promising opportunities ahead. I want to contribute to our country's technological advancements following the vision of His Royal Highness Crown Prince Mohammed bin Salman. His vision inspires me and inspires us all to build a promising future for our nation. And in the end, I believe that together we can shape a future where semiconductors drive progress and innovation for generations to come. Thank you.
Thank you, Fajr and Sarah. And finally, a big thank you to everyone who contributed to organizing this important event, and thanks to all the sincere efforts that made to achieve the highest levels of success during the 3rd edition of this forum. See you all soon in the forum sessions starting shortly, so please be seated. Thank you very much.
Check, check, check. He check. Hello, check. Hello, check. Hello, check. Hello, check. Hello. Hello, check. Hello, hello, check. Hello. Check. Hello, check. Hello, 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 check. Hello, check. Hello, check. Hello, check. Hello, check. Hello, hello. Hello, check. Hello, check. Hello.
Please return to you. Okay, hina. Ladies and gentlemen, we are about to return to our sessions. Please return to your seats. Ladies and gentlemen, we are about to return to our sessions. Please return to your seats. Thank you. Ladies and gentlemen, we are about to return to our sessions. Please return to your seats. Ladies and gentlemen, we are about to begin our sessions. Please return to your seats. For the first plenary lecture, please welcome Professor Shuji Nakamura.
Okay. Okay, so I'd like to talk about big cell, vertical cavity surface emitting laser diode. Okay, I don't know. So this one? Which one? Oh yeah, this is sorry. So, so basically, so laser, two kinds of lasers are available: edge emitting laser or vertical cavity surface emitting laser. So edge emitting laser is used for high power laser, and big cell is low power. Outpower is order of a milliwatt. But big cell is a lot of advantage, especially device processing is very similar to LEDs. So left side LED. So cost of big cell is very, very small. Because HMT laser is the cost, device processing cost is very high. So in the long term, I think big cell would have a huge market because the individual cost also, that's a big difference. So right now, big cell, initially for long time in the past, for a long time, big cell had no market. But Apple computer, Apple iPhone used the big cell arrays for face recognition for the first time. And then now big cell has a huge market, especially face recognition system. Also autonomous vehicle, they like to use a LiDAR as a sensor. So LiDAR also uses a big cell laser, big cell array, So now big cell has a lot of market. So you see, this is big cell arrays. So each big cell is very small. Aperture size is 8 micron or 10 micron. And and the big cell has we need the fabric period cavity. So we need high reflection mirrors. Bottom mirror and top mirror, we use DBR. So conventional mirror, they use epitaxial ground multi-layers. And the left side, a lot of array. In this case, 1,000. So each one has only output is 1 milliwatt or 10 milliwatt. But using array, 1,000 array, it becomes 1 watt. So high power, they can use high power lasers using 2D arrays. And so, yeah, same thing. I skip this one. So big cell, motivation, a lot of advantage, because one of the big advantages, circular beam, circular. So it means circular means the coupling to the fiber is very high but edge emitting laser dyes are not circular, so coupling to the fiber is not so good. And another thing is also, another thing, at UCSB, we use different crystal orientation. Usually, 3 nitride-based laser, we have to use C-plane. But the UCSB, we use different crystal orientation, M-plane or same polar. So in this case, we like to use M-plane to minimize polarization. So, but first big cell was developed in around 2008. 2008. One company, Nichia, and also in Taiwan, NCTU developed the first big cell using a gallium nitride-based material in 2008. But still, no company can make commercial-based big cell. The problem is, problem is threshold current density. JTH is almost 10 kiloampere per centimeter. Also, operating voltage is 3.7 volt. But right now, infrared gallium arsenide big cell is in the market. In that case, threshold current density is less than 1 kiloampere per centimeter. Also, voltage is very low. So input power is very small. But in the case of gallium nitride big cell, input power is very high. So a lot of heat generation. That's the reason no company can make a product. So, input power of the gallium nitride was 20 times higher than the conventional infrared big cells. So that's a big problem to make the commercial-based big cells. So this is a conventional, infrared gallium arsenide big cells. So top DBR mirror and the bottom DBR are epitaxially grown multi-layers. So all of mirrors are grown, epitaxially grown, you know. So that's a big advantage. Also, also another advantage that, these epitaxial grown mirror is gallium arsenide and DBR. Index constants, they are very high. So only they need 20 or 30 multi-layers is required for each mirror. So it's very simple. But in the case of gallium nitride big cells, the problem is we cannot use epitaxial grown DBR mirrors for bottom mirrors. Because in the case, we have to use aluminum indium nitride, gallium nitride DBR. But in this case, index constants is very small. So we have to grow a lot of multi-layers. It takes half a day or 1 day. Also, another technique is that we use direct DBR for other bottom mirrors. But in that case, processing is very complicated. So this time, today, I like to talk about nanoporous gallium nitride DBR as a bottom DBR mirror. So in this case, we can just grow these layers. So it's become much more simpler. So this is a comparison of, currently working for the groups. So Sony, Nichia, and Stanley, also another Yale and Gambix. So these companies are working very hard to develop the commercial-based big set, but still nobody succeeded. But now, top companies are Sony. Sony is recently making a big breakthrough to make a very good, single mode, big cells. Because in the case of gallium nitride big cells, biggest problem is how to make a single mode lasers. So conventionally, we use, cavity length is very short. Cavity length is 1 micron, 2 micron. So in this case, always, transverse mode is a multi-mode. Nobody could make single mode. But the Sony, using a long cavity, they observed the, first time a single mode, stable. Also, yield of the big cell is very high. They claim, almost 100% yield. Conventionally using short cavity, yield is very poor. Also, always multi-mode, so multi-mode, we cannot use it. Yes, so I totally explain, so Sony, okay. So basically, Sony developed a very good big cells using these structures, using a long cavity. Cavity length is 20 micron. Usually, big cells, the cavity length is 1 micron. But they use a long cavity. Also, they put the curved mirror. Because the curved mirror is very important. Because the cavity length is long means the laser beam diffract. If we're using the flat mirror, this reflected laser beam diffract. So diffraction loss become very large. Using curved mirror, we can minimize diffraction loss. So, but this is performance very good. But the problem is processing is very complicated because this is substrate. Substrate is initially 300 micron thickness. They polish to the thickness 20 micron, and they form the curved mirror. So processing is very complicated. That's a big problem of Sony's laser. But the performance is very good. And others are using a short cavity, like 2 micron in this case, and 1 micron. So using a short cavity, it's difficult to achieve the single mode emission. So this is our big cell. Our big cell, we use this one. We use top mirror has a curved mirror. Top mirror, this is a curve. We may use the curved mirror using silicon dioxide material, and we put direct DBR. And the bottom mirror, we use nanoporous DBR, and the cavity length is about 10 micron. And the aperture is made by using the tunnel junction. So our curved mirror is the top side, also using silicon dioxide. This process is very simple, much easier than the Sony's structures. Top has a curved mirror, and the mirror is made by silicon dioxide. So it is very simple structure and a long cavity with a curved mirror. So this is our processing. Basically, cavity length is about 10 micron, and cavity is made by buried ternary junction. And bottom mirror is a nanoporous DBR, and top mirror is just with a curved mirror. No? And the benefit of the long cavity is, so this is compare the short cavity big cell and the long cavity big cells. So short cavity means longitudinal mode is number of longitudinal mode very small. So each delta lambda is very broad. So, but in the case of long cavity, longitudinal mode, a lot of longitudinal mode. So in this case, for example, quantum well thickness is 5 micron. So in this case, quantum well is should be located at the position of the longitudinal mode, no? So, but in this case, using a long cavity, we can locate any place for the quantum well because there are a lot of modes. So yield of the big cell is much higher. Also, another is heat resistance. Using a long cavity, heat resistance becomes much smaller because we can remove the heat from the side wall. Because using a short cavity, it's difficult to remove the heat from the side wall because thickness is very small. Because also DBR is the heat resistance so high, so we can't remove the heat from top and the bottom side, only from side wall, no? So this shows also the diffraction loss. So this is the diffraction loss as a function of the cavity length. So if the cavity length increase, diffraction is very, very large. Especially using the aperture size when the aperture size is small. But using, in our case, we right now use 8 micron or 7 micron aperture. So in that case, diffraction is very small. This is a flat mirror. So flat mirror still, diffraction relatively high because this is a gain, no? So using the curved mirror, we can minimize we can reduce this diffraction dramatically. So that's the reason we need the curved mirror to reduce the diffraction loss. So this shows how to make the curved mirror. Basically, Basically, we use a photoresistor pattern like this, and we increase the temperature of this photoresist up to 135 C. So in this case, this photoresist shape like this. And then using a dry etching, we can dry etch the silicon dioxide like this, so we can make the curved mirror. It's called the reflow, no? And we can make a beautiful curved mirror using silicon dioxide mask. And this is the final structure, so we can make the curved mirror top and the nanoporous DBR here, and we put also another DBR mirror here, no? And the cavity length is about 10 micron. And this shows how to make the nanoporous gun. So just we use the electrical chemical etching. So using the especially using this one, this is the doping concentration, silicon doping concentration as a function applied bias. So basically, high N plus layer is selectively etched, and we can make a beautiful porous gun using this electric chemical etching. And this is bottom nanoporous DBR mirror. You can see the, this is air gap. So so porosity is in this case about 30%. So in this case, so we can make beautiful mirror. So this is red one is a simulation, and blue one is experimental reflection. So you can see we can make beautiful high definition mirrors using a nanoporous gun. So using we can make beautiful big cells, and so you can see this is each one has a big cell. So so yield is very high. Usually university when we make a big cell, only among 200 big cells, only 1 or 2 devices worked. But now about yield is 20%, 20 big cells working using this long cavity with a curved mirror. And so this is a comparison of our UCSB result. So I told you, Sony is right now the best pixels using a long cavity with curved mirror, and threshold current density is about lowest at 9 kiloamperes per centimeter. So, ours UCSB is now, about almost 9 kiloampere, but the power is small. But the latest one is, threshold current density is 1.4 kiloampere, almost 1 kiloampere per centimeter. It's very good. But this one is multimode because we use special structures. But very interesting, threshold current is very low. But others, you can see threshold current very high. But this graph shows the threshold current of 0.7, but no result of power and no mode. But ours is, power is relatively high. But problem multimode, I explain more detail later. So sometimes we observe the multimode, but the multimode caused by the strange over-etching of the nanoporous gun. So nanoporous gun should be here like this, but sometimes over-etched like this. So in this case, nanoporous DBR shows some strange reflection. It causes a multimode like this. So we know the origin of the multimode. But anyway, we can make a beautiful CW laser by controlling the long channels. So usually we obtain the very beautiful single mode emission, when the nanoporous gun is it's etching, we don't have any etching problem. So you can see beautiful Gaussian profile and the single mode. So using a long cavity. And also recently, I told you, we observed a very threshold current, almost 1 kiloampere centimeter, usually about 10 kiloampere, no? But in this case, we use a special structure, but also, in this case, multimode. But the special structure means we made the hole like this. So here is the aperture, surrounding the aperture, we make a hole, like a photonic crystal. So, but in this case, lateral confinement is too strong. That's the reason it becomes multimode. But the threshold current density is 1 kiloampere. It's a world record. By controlling this lateral confinement, we can reduce the threshold current density dramatically. So that's all. Thank you.
Ladies and gentlemen, next, please welcome to the stage the keynote speaker, Dr. Naveed Sharwani.
Assalamu alaikum, everyone. I think we gave a small preview of this initiative called National Semiconductor Hub. In the next 10 minutes, 15 minutes, what I would like to give you more details about what this whole idea is about and how do we plan to go about it. This initiative started a year ago when we started thinking, is there a natural place in the world where we could build the next generation of semiconductor companies? We felt that it has to have 3 essential ingredients. Number 1, the leadership of the country should have the vision to build something like that. I never thought my speech could start fire alarms, but I now know that I can do that. So, by the way, if you think that was accident, no, that was planned part of the whole idea. If you are not paying attention, to wake you up. So apparently it's working quite well. Okay, so to focusing on as I said, we said that there has to be three things for this to happen. Number one, the leadership should have the vision. And we believe we have the leadership here, we have the vision. Number two, we should have the capital that it takes, patient capital. Semiconductor companies cannot be done in 3 months, 6 months, 1 year, 2 years, 5 years. It takes a long time. And third thing, there should be the rest of the ecosystem that is being built. With so much industrial development that is going on here, our companies can get the boost because they can supply into the overall ecosystem. There is only one place in the world where this is happening today. And this is how we ended up here. It is not an accident that we ended up here. So what are our goals? Our number one goal is to get 50 fabulous companies here over the next 5 to 6 years, Vision 2030. People used to ask me, 50 companies, how many companies do you have now? My answer is very simple. Break down your task into smaller tasks. So what is the task for this year? Bring 5 companies. And I said earlier, we already have 3 companies registered, and today we have 12 to 14 companies talking to us that they would like to join us. And we have only 2 more slots available for this year, and we have 14 companies who want to join us. I don't think it is a very big ask that in the next 5 to 6 years, can we get 50 high-quality, good companies here? When I say high quality, what do I mean? I mean the companies we build here are not companies that are aiming to replace NVIDIA. We are not trying to challenge AMD and Intel. No. We are not working on any controversial chips. We are going to build chips that is needed in life, in industry, that makes our country and tick. Secondly, these are those companies that will take advantage of our central location to attract global talent, global technology, and then build chips, not for the kingdom and the region, but for the global markets. What we are hoping is by sitting here, we can ship to every region of the world. That is a huge advantage we have. Why we are coming here? We want to come to Saudi Arabia and start all these companies because we want access to global markets. So those are the companies. Of course, these companies will not be started without the right kind of people. So we need 25 experts. We have very large number of experts. In fact, Dr. Munir has promised me that he has 3 experts that he is going to have, and I am looking towards him and looking towards all these experts. So, and inshallah, we already have 2 experts. Third thing, we have to hire 5,000 engineers. And I'll talk to you about how you plan to do that. But we are hoping that between these 50 companies, the total value created is you should exceed 50 billion. So here's our program. How do you make this program successful? There are 4 essential pillars that we'll have to work on. We'll have work on building a team of 5,000 people over the next 5-6 years. They will not all be here. They will be in different locations in the kingdom, and many of them will be in design centers in neighboring countries, neighboring friendly countries. Secondly, we have to have a very good system of finding the best companies in the world. We will go look for them. We're not going to sit here and wait. We'll go to every place in the world where there is any interesting, fabulous companies, and we'll try to see how they can join us. We will have a very strict evaluation process from technology, markets, team, why these companies can come here. We will have the world best incentive program. I want to ensure you that if you bring your company here, me and my team will take care of you from relocation, from salary, from startup fund, from any other aspect of incentives we can provide you, we will work with you. And the last thing is we need to have the infrastructure. I'll talk about that. So let's start with the human talent. Well, if you think about, we have to train 5,000 and relocate 5,000 people. And today in design, around 200,000 people work around the world. So it looks like a small number. It is not a small number. It's a very big number for us. Why? There are no 5,000 people here today. And we have no capacity to produce 5,000 people here today in a short term. So what we have to do, we have to gather all the key universities of the kingdom and look at all the surrounding neighboring countries and then build an education program. We have already started one. We have started 2 such programs already. Our goal is to have 500 people ready to join our companies in the next 12 months. Inshallah, we already have a line of sight how we can train and get these 500 high-quality people. 25 experts. Why do we need these 25 experts? One of the greatest things we have in Silicon Valley, you have a packaging problem, you can go talk to somebody. You have a test problem, you can talk to somebody. You have a fundraising problem, you can talk to somebody. Those experts play a very, very important role why Silicon Valley became Silicon Valley. We need them here. These people will do 3 essential things for us. Number 1, they will give us a vision. What kind of companies should be coming here? 2, they will advise our founders, how can they grow in their careers, how can they lead their companies. And 3rd, they will solve day-to-day problems of the companies that they cannot be solved by the team because they don't have the 25, 30, 40 years experience. And the last thing these experts will do is to be an eye out for us, all the stakeholders. Are the companies progressing as they should? So that's a very important aspect they will play. The next thing is, how do we plan to get these companies? So we are already planning 2 conferences around the world. Then we will have the road shows. The whole idea is that we have kept our goal low. If you think about that, only 5 this year, and we already have 3, so we need 2 more. And we have many, many applicants. Next year, inshallah, we want to get 10 companies. It is my goal that I want to have an application funnel of close to 50 to 60 companies from which we want to choose the 10. This is how we will ensure we will the high quality companies. We have a complete process for selecting, which I'll tell you about. The 3rd thing is funding. For funding, and this is His Excellency Abdullah Swaha, he's taken a direct responsibility. He said, we are going to make sure that the kingdom is committed to funding all these startups that we are going to have, or the companies we are getting. So far, we have 3 companies. We don't have the fund yet. It's being set up. First company has received a term sheet for $30 million. Second company has received a term sheet for $12.5 million. And another company has received another term sheet for $12.5 million in last 1 month without the fund. So there is enough capacity in the VC infrastructure for almost $60 million of funding, at least in term sheets, without the fund. So this means that the consortium that we want to build, and we want to include, I think our friends from Ajlan are here, Olayan are here, NEOM are here, PIF are here, Aramco are here, Wayed are here. All of them are here. The idea is let's combine all of them into a consortium to help support these companies. The last, and I talked about that incentives, we are working with National Technology Development Program, Ibrahim and his team, wonderful people. They currently have 18 incentives that they offer to companies. But what we are doing is we are building a special program called Fabulous Semiconductor Design Program. It is a collection of 10 incentives that you can get. And what are those incentives? You are relocating, we have some fund for you. If you hire some Saudi engineers, we have fund for you. If your founder is a Saudi, we have some funds for you. You have received some funding, we can give you a loan. If you have received a term sheet, we can give you about half of the money in the term sheet as a loan until you get your money from the term sheet. There are many, many incentives. Let me tell you, no such incentives are available in any part of the world. I know that. I have been in this field for over 40 years. They are not available in China, they're not available in India, they're not available in US. We are going to put together the world #1 incentive plan. People should come here, founders should come here because of our incentive plan. And secondly, it is my commitment and my team's commitment, we will solve individual problem of the companies. If you have a specific issue, come to us, we will find the solution. You can't find a talent, we'll find the talent. If you can't find an IP, we'll find an IP for you. So it's not about a set program and we let you go. No, we are your partners. We will make you successful. If we don't make them successful, we don't have anybody else. So this has to be our mindset as we bring the companies here. About the infrastructure, we already have a company called Epic Semi. So Epic Semi is going to provide entire back-end infrastructure, meaning if you want physical design, if you want masks, multi-part wafer, you need prototypes, load boards, or you need any support in terms of sales, marketing, logistics services, you need to ship your chips anywhere in the world, we have Epic. And what does Epic do? Well, if you look at China, they have companies like that. You look at Taiwan, they have companies like that. If you look at Santa Clara, Silicon Valley, we need to have a company like that. So we will have that company, the company is already here. And actually, we are expecting that company to have a revenue of over 30 million this year. Why? Because that company is already here, we are already providing these services. Now, if you look at that base company, the verticals are all the different companies that will come in. And what is the benefit? Each company does not have to have a back-end team. Each company does not have to have a package team. Each company does not need to think about how will I get the wafers, how do I talk to TSMC, because we will do that, because Epic will do that. So this is our very simple funnel that we want to, that without boring you with the details, we want to have a very, very elaborate process. How does a company come in? We don't want a company to come in and then struggle. We don't want a company that can't sell. We don't want a company that cannot find a right talent. We do not want a company that cannot raise the money. We do not want a company that will struggle. It is a very tough process. So we want to make sure when the company is here, it is here because we can get them the funding. It is here because I can get them the people. Because they're here because I can get them the manufacturing. What's the point of bringing a company here and they need 3 nanometer process and we have no access to 3 nanometer process sitting here on certain fab? There would be no point of doing that, right? So this funneling process is a lot more elaborate than just looking at the company structure or doing the due diligence that VCs do. We intend to provide that kind of process. So in conclusion, I just want to say that this is a very, very bold initiative by the kingdom. And I can also say that's not an easy initiative. It's not going to happen because we can give speeches and we can give presentations. It is going to happen because we have to do a lot of work on the ground. We need a partnership from everybody in the kingdom, but we also need partnership from many, many international partners. We are talking to people like TSMC, ASC, you name it. We are talking to all of those partners because they have to support our companies. But I can tell you one thing. When I came here, my first host in this country was Dr. Munir. My first office was in KACST. It still is in Building 17. I'm very thankful to KACST. This particular initiative would be nowhere. It was simply not possible. In fact, when I came to the kingdom, I met Dr. Munir for the first time, and Dr. Munir said, Dr. Shavani, whatever you need, what I can do or my staff can do, we will make it happen for you. So Dr. Munir, I'm very thankful for you, and this initiative is very thankful to you. Thank you very much.
Ladies and gentlemen, next, our keynote speaker. Please welcome to the stage Mr. Sunil Banwari.
Marhaba, good afternoon, everyone. And I know it's getting closer to lunch, so I'll try to be efficient. First of all, I want to, on behalf of Ajlan Brothers, I want to thank for this opportunity, His Royal Highness, Crown Prince, for the opportunity to be part of Vision 2030 and drive the semiconductor transformation on behalf of Ajlan Brothers. I also want to thank the chairman of Ajlan Brothers, Ajlan bin Abdulaziz, Vice Chairman Mohammed bin Abdulaziz, and Executive Director Fahad bin Abdulaziz. Again, what I bring to the table is I've been in the semiconductor industry for 36 years. I was with Intel for 20 years, on Semi for 7 years, and I'm excited at the opportunity to talk about how we can bring semiconductors value chain to the kingdom today and in the future. So, again, I will talk about the question which is commonly asked in a conference like this is semiconductors the new oil? Now, what's common between semiconductors and oil is a $1 trillion plus economy. Well, semiconductors is headed in the same direction. Semiconductors is also heading to be a $1 trillion economy. The growth rate is phenomenal. It's anywhere from 6 to 13%, depending on the sector. And that's very important. Within semiconductors, there are multiple sectors, automotive, mobile, et cetera. And again, it's important to have a strategy for each sector. So one example, I think this week you may have heard, the AI chips are growing at 33% just in this year. So based on that growth, a company like NVIDIA, which had a market cap, which was only $300 million, this year, in 1 year, NVIDIA has added the market cap, which is the same as Saudi Arabia's GDP. So Saudi Arabia's GDP of 2.3 trillion is exactly what NVIDIA has added to its own market cap. Tells you the phenomenal growth the industry is experiencing. So when I talk about the different sectors, I think it's very important to talk about how can we address those sectors, and there's no one size fits all. You need a different strategy for each sector. So what we have done is we have engaged with multiple companies who are prospective partners in different stages of transactions. So again, what we are trying to do is cover the design, wafer fab, assembly test for each of the segments, whether it's sensors, storage, automotive, et cetera. So that basically our goal is to have a comprehensive end-to-end strategy for the kingdom in conjunction with our partners. I'll spend a little bit of time talking about the value pyramid for semiconductors. So if you look at the value pyramid, the most advanced or the highest value is semiconductor design. My colleague, Dr. Naveed, talked about the design challenges, the new initiative on National Semiconductor Hub. That has the highest value add. 50% of the value add plus comes from the design. That's why you find companies like Apple, NVIDIA have very high market cap because they keep most of the value. Right behind that, number 2, is the wafer fab. These are the multi-billion-dollar investments made by companies like TSMC, which are building massive fabs all over the world. That's followed by assembly and test, which is another 10% of the value chain. So if you look at these three, you can see clearly that we have to have a strategy for all of these pieces, not today, but in the future, so we can address eventually and create an end-to-end supply chain which allows the kingdom, as part of Vision 2030, to be somewhat self-sufficient and immune to the geopolitical pressures, as well as drive the vision of having Saudi Arabia being the 15th largest GDP in the world and 50% of the revenue being not oil-based. Our thoughts on how do we get to this roadmap, right? This won't happen overnight, and this has multiple elements we need to consider, and this is what we are working on at Ajlan Brothers. The first piece is we really have to understand the semiconductor industry. What is the industry, key sectors? What is our strategies specific to each sector? How are we going to engage? So if you take the example of design, in the case of design, again, our goal is we will not be Apple or NVIDIA overnight. But what we can do is partner with the National Semiconductor Hub and work to support Dr. Naveed's vision and His Excellency Al-Swaha's vision. And that's what we are doing. We are working closely to support 2 of the 3 companies which Dr. Naveed announced. We are working with him closely to enable and see how we can partner for success. From an infrastructure and manufacturing side, we are talking to leading companies in the world which have their own fabs, which rely on foundries, and we're even working with companies which design the clean rooms for those factories so that we can have a comprehensive structure. And this is one which we can work on today, whereas for design, we need to start small with the smaller investments, and I'll talk about this in the subsequent slides as well. We need to foster research and innovation and develop a skilled workforce. This is a topic which KACST, KAUST, RDI know very well. We are here to support you. We are here to reap the benefits of all the efforts KACST and KAUST and RDI is doing in this area. The workforce development, creating the dedicated engineers, that's exactly what a country needs, which is trying to go down this journey. Developing collaborative partnerships. We are working with PIF, NDD, to understand the demand forecast because, again, we don't want to build factories when there's no demand. We want to make sure whatever we are building is aligned to at least what the kingdom needs, and eventually the Middle East, MENA market, and beyond that. But understanding what the market is will make sure that the investments we are making in factories today will have customers in the future. So that's another part of our vision. We are working with the automotive sector, for instance, to understand the engagement, the goal of developing 440,000 cars a year in the kingdom. How do we enable the semiconductors to support the vision of building those cars and have the semiconductors be made in the kingdom? Leveraging government support, we are working with the ministries. We are working with Sharik, MCIT, Sharik, MIMR have been very helpful, helping us understand the incentives, discussing how we benchmark the incentives to the rest of the world. This is, again, a very good collaboration. Again, as Dr. Naveed mentioned, in the kingdom, we have a very good incentive system for attracting design companies. We want to end up with the same situation in the manufacturing space, which is where the discussions are. And finally, adopting a fabless business model. This is what we need to do. We invest in the simpler designs, which eventually give us the capability to try more and more ambitious designs in the future. So just example of why do we need to foster research and innovation? If you talk about, a lot of people think about semiconductors as silicon. But nowadays, there's new material like silicon carbide, gallium nitride, and the growth rate is phenomenal. So these are areas where we need to have local manufacturing so we can support the automotive industry of the future, especially since at least 2 companies in the kingdom, Sear and Lucid, are building electric vehicles which need silicon carbide. So if you look at it, what we are doing is we are partnering with an industry leader in silicon carbide. That company is working on 8-inch wafer technology today, whereas most of the world is still using 6-inch wafers for silicon carbide. But we are actually trying to get ahead of the curve, so we are ready with the latest technology. We don't want to work on yesterday's technology. We want to work on tomorrow's technology today. So that's what we are doing by partnering with industry leaders in silicon carbide space. Investing in infrastructure and manufacturing. Now, I want to make an important point here. When we build factories in the kingdom, it's very possible when we build factories in the kingdom that these factories are either too big or too small. How do we know what the size of the factory should be? we have data from that. This is a study from McKinsey, which tells us that there's an optimum level. If you have 600,000 layer starts per week, that's just enough to give you the right economy of scale for a semiconductor factory to be successful. So we have to target the minimum because we are not TSMC. We will not be building the world's largest factory. But if we develop the right factory plan at scale, which makes us cost competitive, then we will have a bright future. So again, leveraging the information out there, leveraging the benchmarks, coming up with the right size, building factories which are neither too small nor too large is the intent. And again, hitting the right scale is very important when it comes to manufacturing. Fabless business model, I think Dr. Naveed has spoken about it enough. But one thing I want to emphasize, the kind of design companies which Dr. Naveed is working on are still at the less advanced nodes. Now, you know in semiconductors, it's very important to be building at the 2 nanometer, 3 nanometer. But to build factories, design companies which do 2 nanometers, you need investment in the billion-dollar range. Today, we are starting small with the lower nodes, so we can start learning the process, developing the expertise in the kingdom, and the investments are small enough that they can accommodate in the garage. But as we get more proficient, the scale of investment in design will go up over time. That's based on studies. So as we start today with 16 nanometers plus, that's a good way to learn and get capable. So down the road, we will be developing more advanced designs, and it's foolish to think that tomorrow we could be designing chips for the iPhone. That's not going to happen. But if we start with the simpler chips which are on the iPhone, and then over time build the heart of the iPhone, that's very much possible. So I think that's the scale. So you have to scale our vision to our capabilities and develop it over time, which I think this country is doing. So I'm very optimistic about the initiatives announced today and how it supports the global vision. And we are very much happy to associate with the design element of the value chain. So I think some of you must have gotten intimidated. You must have seen me talk about semiconductors are too difficult. You have to do design, you have to do manufacturing, you have to do assembly test. It's a lot of work. But the good news is there's no country in the world which does all of them very well. Not a single country. Taiwan is very good on wafer fabs. US is very good on designs. But not everybody is good on everything. So we have time to catch up. If you look at these bars showing that there is pockets of competency across the world, starting off the bat, we don't have to be good at everything. So we can start and pick our spots, over time scale and become better. And that's the semiconductor journey for the kingdom. Finally, another thing I want to point out is, again, you've seen me talk about a lot of efforts in progress. But the question you must have in your mind is, how soon will we have a factory in the kingdom? So I think it's closer than you think. We actually submitted a proposal in February to the ministries, and we are working closely. We have very good support from them. We are working to make sure we benchmark the incentives and in the process of finalizing. But the important thing to notice is, even though the number of jobs created by this is only less than 500 jobs, so only 500 jobs created with a $400 million investment, sounds very small. But there's a study done in the US that for every job, for a single job created in semiconductors, 5.7 jobs are created in the broader economy. So think about it. That's the multiplier effect, not just in jobs, in revenues. All these companies will generate revenue. There'll be ancillary companies. People like in this audience might be thinking of how to become a supplier to these companies. So that's the multiplier effect to the economy, which we can plan for. And I think that's the key part I want to emphasize. So with that, I'm getting some nasty looks. I'm out of time. So shukran, thank you very much, and appreciate your time.
Ladies and gentlemen, next, we have our keynote speaker. Please welcome Mr. Ross Jato.
Your Excellencies, ladies and gentlemen, good afternoon. أهلا وسهلا. أنا سعيد جدا أكون موجود معاكم هذا اليوم ومتحمس أكون قسم يعني جزء من التمكين semiconductor صناعة semiconductor بالمملكة العربية السعودية. I'll say the rest in English. I haven't spoken Arabic in 40 years, so excuse me. All right, well, it gives me great pleasure to be with you. I will be talking about our journey together in bringing semiconductor manufacturing, design and manufacturing to the kingdom. You heard Dr. Naveed and Sunil talk about how enthusiastic they are about this segment, and I will talk further about this and what we plan to do. All right. So first, I'm quite bullish also on semiconductors in the kingdom. And we can rattle off why the KSA is well positioned to be an active and integral part of contributors in this industry. But the proof is really what the world thinks of the KSA. Minister of Investment recently at the Melkin Institute conference said it very eloquently, Minister Falah. In the past 3 years, while the world's direct investment, foreign direct investment, declined by 38%, the foreign direct investment in the kingdom doubled, basically increased by 100. That's the best testament of what the world thinks of the KSA and how they're ready to invest here. So we don't need to tell you, the world is telling you that this is the right place to do it. So we should all be very proud of that. Now, one may argue, does that translate into a success in the semiconductor industry? You know, capital infusion and stability are a prerequisite, and certainly that's there. But the resources, the talent, the energy, the infrastructure, is that really there? And I'm hoping in the next 5 minutes, I think I have 10 minutes to speak, to convince you that that's the case. Now, one way that I look at semiconductor manufacturing feasibility and the success of it is I look at the top 3 resources to me that are super critical, and that's water, energy, and talent. Water, energy, and talent. So for short, wet. The wetness of a country when it comes to semiconductor production. So I'm hoping to convince you that from a semiconductor point of view, Saudi Arabia is actually a very wet country. All right? So water, energy, and talent. So let's talk about those 3 things. So don't pay attention to the numbers. Those are quarterly revenues from 22. But this is kind of showing the pure play foundry business and the distribution of it. Now, when we look at this wet figure of merit, we always have to look at it comparatively or relatively. The amount of water, energy, and talent we need, or we have to have, is meaningless unless we know how much water, energy, and talent we need. Our goal at Alet is to be able to produce 1 million 12-inch wafers by 2030 annually. When you compare that to the world, there's about 300 million 12-inch wafers annually. So we're going to produce 1, the world is producing 300, and you can see the distribution. So some companies in Taiwan are producing 30 million or more. So the amount of water we need should be scaled to the amount of production we will have. So we've done the analysis and we've worked with some of the ministries. In fact, the KSA has sufficient water to meet 10 times our demand by 2030. 10 times. And as you know, semiconductors is a very water-intensive process. A semiconductor the size of your fingernail on your pinky takes 30 liters of water, ultra-pure water, more pure than drinking water. So it's a lot of water, but that water needs desalination and multi-stage filtering that requires energy. So water is energy, and we have an abundance of that energy So much so that we can go actually to 10 million wafers. We have that level of energy. Speaking of energy, we go to the E in energy. We have one of the best cost structures for energy of renewable energy at about 1 cent per kilowatt hour or less. And the backup energy, the traditional energy, at less than 5 cents per kilowatt hour. So that's kind of the range we're talking about, and we're well suited for the cyclicality that semiconductor industry sees. So when there's a lot of capacity and we see price erosion, whoever has the lowest cost is the winner, and we are well positioned for that. Finally, let's talk about talent. A lot of people talk about talent. For a semiconductor manufacturing of 1 million wafers per year, what is the talent input into that? So according to the Ministry of Education, we have about 1.4 million higher education enrollments in the kingdom. That is actually higher than countries like Taiwan, Singapore, Ireland, that has many fabs. So the number of higher education enrollments we have is higher than countries that have to feed 30 million wafers a year or more, while we're trying to feed 1. So it's all a supply and demand problem. And so when you look at all these three and compare the kingdom to other leading semiconductor industries, our wetness is 10 to 20x higher. So my argument is the kingdom is well positioned to have the resources necessary to succeed. I hope I've convinced you of that. Now, what are we going to build? And what is, I think Sunil mentioned, we want to build what's needed for tomorrow. So as we set up our manufacturing, as I mentioned, we will be setting up front-end and back-end manufacturing in the kingdom, inshallah, for 1 million wafers per year and grow from there. What are we going to build? So this is the future of semiconductor forum, so I felt like I should give my opinion on where the semiconductor industry is going. In the past, semiconductors wanted to be discrete to application-specific items. So a CPU is a CPU, a GPU is a GPU, and you optimize. Then there was SoCs where you integrated logic device together. But still, there was technologies that stayed. Memory by itself, SoCs by themselves, analog digital converters by themselves. And you optimize and make the package because it was optimized for cost. Now we're optimizing for performance and value. What that does is bringing technologies together. So I argue that the world is going towards more technology integration. Very different technologies coming together. So as an example, I'll use something that all of you use every day. In fact, I see a lot of you with your cell phones taking pictures. So in every one of those phones, there's at least 4 image sensors. When you get in the car, you have a rear view camera. That's the selfie of the car, just like the selfie that you carry with you. So you're using these every day. So let's take that as an example of technology integration. First of all, the wafer is still a thin wafer, okay? But in it are many, many layers, easily 60 mask layers. It's made up of 2 wafers that are hybrid bonded. The bottom wafer may be at what node? 28 nanometer. The top wafer may be at 65 nanometers, so mix of technologies. At the top, you have anti-reflective coating to the angstrom level with many layers, and I'm still just at the top. Many layers at the angstrom level to block some frequencies and to let some frequencies. Afterwards, I think Professor Nakamura, you were talking about lenses. Here are micro lenses. There are millions of micro lenses inside each one of those chips. They have to be the same, not only in the chip, but chip to chip. You can't have your phone take a different picture than someone else's phone. They have to be exact and accurate. 100 of those lenses, if you stack them against each other, is still thinner than one of your hairs. That's how small these lenses are. Then color filters, then you get into photo diodes. So here is optical, analog, digital coming together And at the bottom, I hope you can see it, there's an ASIC. What the future holds there is you see a lot more compute going in there. Processors, image signal processors, ARM cores, and now we see AI engines going in there. Now the AI engines are there to improve the sensor with time. So unlike our human eyes that age with time, and we don't see as well as we age, these sensors actually get better with time. As the world learns more about corner cases and looking at night and at corner cases, new weights are loaded into the sensor and it becomes a better digital eye with time. So that's the world we're going into, and this is just an example of where the future is going. And this is still a single component. You see a lot in data centers where you have multi-chips going onto a one silicon interposer. The high bandwidth memory with a CPU and others all coming together. So I argue the future is where you integrate many technologies together that in the past were considered very different. Now, this is pretty sophisticated, as you can see, and sometimes we take it for granted. And it's in everybody's phone and everybody's car, and we have it everywhere. Alet will not be able to do this alone. As the saying goes, it takes a village to raise a child. And luckily, with the National Semiconductor Hub that Dr. Naveed spoke, and the support of KAUST and KACST, and the guidance of the MCIT, we're going to make that happen. We really need many companies working together. I spent more than 2 decades, nearly 3 decades in Silicon Valley. I can tell you the history there with Fairchild and Stanford, creating the Silicon Valley and creating the Fairchildren, the Intels and the Apples and the AMDs of the world that came out of one company, Fairchild, took about 2 decades. Well, we're going to accelerate that with the National Semiconductor Hub, with the guidance of MCIT and KAUST, KACST, and Dr. Naveed. And Alet certainly is right there with you, and we'll support you on that. At this point, I think I've probably exhausted my 10 minutes. Thank you very much, and I look forward to working with you in the future. Thank you.
Ladies and gentlemen, next, please welcome to the stage keynote speaker, Mr. Ibrahim Niaz.
السلام عليكم. السلام عليكم ورحمة الله. Can you hear me? Perfect. So I prefer to use the mic and move on the stage rather than staying behind the podium. So to be close to you. Good morning, everyone, or good afternoon. My name is Ibrahim Niaz, and I'm the CEO of the National Technology Development Program, NTDP. I spent almost 2 years right now in this role. And until today, I cannot say the name of the program in Arabic correctly. We have the longest name among all other government programs. It's not like Ross, he has like just one word, Alet, either in Arabic or English. NTDP is a government program and with a mandate of developing, uplifting, and stimulating the technology ecosystem here in Saudi Arabia. We operate as a development fund with a $700 million, 2.5 billion riyal, to build and uplift and develop this sector with more focus toward building the tech startup ecosystem and also with more focusing toward building the emerging tech and deep tech industry here in Saudi Arabia. With our mandate, we have 3 main objectives. First of all is to developing the Saudi tech sector where we contribute in the GDP of the tech sector and also increase the job in this sector. The second objective is to driving sustainable growth for the private sector, either through supporting the startups across all the stages or working with tech SMEs, the small and medium enterprises, or working with enterprises and corporates here in Saudi Arabia through providing a range of incentives. Most of our products are financial driven products between grants, subsidies, and also loans. Third, to position KSA as a global tech hub and a launch pad for tech startup from Saudi Arabia. So we are in NTDB, we work as a catalyst with, as I said, with the tech startup ecosystem. So we work with everyone in the ecosystem. We work with all VC funds, private equities, angel investors. We work with commercial banks, financial institutes. We work with enterprises and corporates. And also we work with accelerators, incubators, globally and locally. And we work to support the entrepreneurs and to support the startups across all the stages. As we speak today, we have around 45 partners. Most of them are from the private sector. They work with us to operate all our products that we have in our portfolio. So as I said, we support the startup ecosystem from pre-money stage to a pre-IPO stage. For each stage, we have a specific products to support the entrepreneurs, to support the founders, and to support the startups. Also, as I said, we support the tech SMEs, and we support the enterprises and corporates here in Saudi Arabia. As we speak today, we have 18 products in our portfolio. Most of our products are financial products, and most of our financial products are grant. It means non-dilutive, non-retainable. And also we have subsidies, we have venture debt, direct and indirect lending, and also we have a guarantees program plus building talent development activities. So for the salary subsidy, we have two products. It's called Boost and Tech Crew. Boost, where we support the founders of the startups if they would like to quit their job and focus on their startups. We provide up to 3 co-founders per startup. We provide them a 1-year salary from the program and support them to grow their startups. Also, we have another program, it's called Tech Crew, where we support the startups, SMEs, and enterprises to cover the 50% of the Saudi tech talents. We cover 50% of their salaries for 18 months. Also, we have innovation support products. We have MVP Lab, where we target the entrepreneurs with a prototype or MVP, and we provide them with grants, and also we put them in incubation in collaboration with Garage, Center of Digital Entrepreneurs, and other accelerators to help them to build their startups and also go to the market. We have AIM, AI Mission, in collaboration with KAUST, Sadaya, MCIT, to build and develop the generative AI ecosystem here in Saudi Arabia. Also, we have Next Era. Next Era is a subsidy or a grant from the program to cover 70% of any R&D grants that the startup or the company would like to do, either in deep tech or emerging tech. As we speak today, we support more than 40 startups in Saudi Arabia with a total of around 99 million riyal. Lead It, it's a talent development program where we build talents either in generative AI, semiconductor, machine language, and etc. Investments, we have FundSwift, where we support the startups when they close an investment round. We provide them with a loan of 50% of that investment round with a 2.5 interest rate for 6 months. And also we have Fuel, it's a fund-to-fund with a 1 billion riyal in collaboration with SVC to invest in funds that invest in emerging tech and deep tech. And as we speak today, we identify a couple of verticals under that fund: space technologies, generative AI, biotech, semiconductor, smart cities, and also Open RAN and quantum computing. Debt financing, we have a LendTech. It's a lending program with a 5% interest rate, 6 months grace period, and you pay the loan over 5 years. We have a loan guarantee. We become a guarantee to the company or to the startup up to 90% of that loan if they take any loan from commercial banks. And also we have a venture debt program. Also, we have access to the market products. We have Connect, where we support the startups and tech SMEs to get contracts from enterprises or corporates or government entities or semi-government. If they got the first contract from any of these entities, we cover 50% of that contract from our side as a grant. And also we have the relocation program where we support global startups, multinational companies to relocate their main HQ here in Saudi Arabia. As we speak today, we relocated 91 startups and multinational companies since last year. We provide them with financial support, financial incentives, and also we give them access to the market and access to our products, portfolio of products. Also, we have Bridge. Bridge is the opposite of relocate, where we help the local startups and SMEs to expand to global markets, where we provide up to 5 million riyal as a grant to help these companies to grow to global market. Also, we have, from enablement point of view, we have Source Tech, where we help the outsourcing companies to increase or recruit talents from cities around the kingdom. Transform Plus, where we help the startups and SMEs to adopt cloud solutions, and we provide up to 1 million riyal as a grant to help them to adopt the cloud solution. And finally, we have the growth support. We have the Unicorn program in collaboration with MCIT, and also we have as a partner, MISC. Finally, we have Empowering Accelerator, where we target to bring global accelerators to have presence here in Saudi Arabia. The offering, we cover 75% of the operation cost for the accelerator, but they have to build an acceleration fund and invest in all startups that they accelerate. As we speak today, from economy point of view, we achieved around 6 billion riyal as additional GDP impact through the tech sector. We created more than 7.3 thousand direct jobs in the market. As a VC fund, our portfolio companies raised more than 2.8 billion riyal, and it's 54 startups raised next round, not 45. And also we unlocked more than 3 billion riyal as a financing, debt financing from the private sector through commercial banks and financial institutes. I remember this number was around 400 million riyal in 2021. At that time, commercial banks, financial institutes, they don't use to provide loans to the tech ecosystem. With our support, we unlocked more than 3 billion riyal. We supported more than 800 companies. We created more than 350 new startups in the ecosystem since last year. We have 19 products, more than 40 ecosystem partners, and we have 8 leading international accelerators. They relocate here. They have presence here in Saudi Arabia. And as I said, we relocated more than 91 startups, tech startups, Series A and above, and multinational companies to Saudi Arabia. Last year, we were focusing on supporting the whole tech ecosystem with a mass movement. We are sector agnostic. Anything that related to tech, we supported. But since the beginning of 2024, we started to focus to build verticals. As you saw, we launched AIM to focus on the generative AI in collaboration with Sadaya and KAUST. And also, we are focusing to build the biotech ecosystem. We are focusing to build the proptech ecosystem, the fintech ecosystem in Saudi Arabia. So in collaboration right now with Research, Development and Innovation Authority, with KACST, with Dr. Nafid and Dr. Shafi, we are going to do the same for the National Semiconductor Hub. We are working right now with them to design an incentive programs to support the semiconductor companies here in Saudi Arabia. Either they are local companies or attracting global companies. Meanwhile, while we are designing this, any company that work in the semiconductor industry, they can get a benefit from all our products that I just presented. You can go to our website, ntdb.sa, and you see all the products, or you can talk to me or talk to Dr. Nafid how to apply to our different products that we can support you through. Thank you so much.
Ladies and gentlemen, next is the panel discussion about the Kingdom Semiconductors landscape, navigating opportunities and shaping the future. Please welcome to the stage Mr. Abdulaziz Shafi, Professor Ian Campbell, Dr. Saeed Al-Shehri, Professor Muhammad Jamaldeen, and Mr. Sunil Banwari, moderated by Dr. Thamir Tabbakh.
Yeah, I'm audible to you guys. Hello, everyone. Thank you for coming. So actually, my first question is addresses to Dr. Saeed Al-Shehri. So Dr. Saeed, how you see KACST is contributing to the ecosystem of semiconductors industry in Saudi Arabia?
Dr. Thamir, and just before answering this question, let me just explain the KACST functions, the KACST mandates in terms of the R&D. Of course, KACST is the national lab that focus on applied research, industrial-oriented research, is mission-oriented, and of course set the national assets for some strategic areas, including semiconductors. And the other functions, of course, is to the science park, where we try to promote the commercialization, close the cycle of the RDI, and of course, try to create an innovation hub by bringing all the key players together, VCs, the deep tech, and scientists. So KACST has more than 100 labs, some of them serving, of course, semiconductors. And in terms of the KACST capability or the KACST activity and effort for semiconductors, of course, KACST, from infrastructure and R&D perspective, they launched, as His Excellency mentioned today in the morning, the 1,600 meter square clean room, state of the art, and it's totally open, has open access to all the R&D and entrepreneurs and of course the RDI ecosystem. And of course today we announce the joint capability with KAUST to even serve and promote the semiconductors R&D startups and enable them and enable the R&D to have full access to the 3,600 meter square state-of-the-art clean room. And from the talent perspective, KACST launched the Saudi Semiconductor program, and that was in 2022. And the aim of this program actually is to enable the R&D in the local universities and build the talent or capability on the IC design. So till now we have more than 18 Saudi universities joining the program. Last year we training more than 450 Saudi student engineers and researchers on the IC design technologies. And of course today we announced the joint or the first master degree dedicated for semiconductors, and of course that will add to the target of having talent in both design and manufacturing. And in terms of our network, I think we can't do everything alone. We have a great collaboration locally with KAUST and Alet and other entities actually to promote the RDI and semiconductors. And of course internationally we are very proud to have two joint centers of excellence with UCLA and University of California, Santa Barbara. And this is 10 years joint collaboration, and we achieved lots of amazing stuff. And we sent some of our people, they graduated from there, and now they are serving actually, it's not only in KACST, but across the ecosystem. I think in terms of the semiconductor, we need to work together nationally and internationally to achieve the target. Today we have Alet, is the national champion for manufacturing, and today also the RIDIA, Research Development and Authority, they announced the new initiative, the National Semiconductor Hub, to support or to create IC design cluster in the kingdom. And the plan is to reallocate more than 50 companies by 2030. Of course, this is in collaboration with all the stakeholders, KAUST, Alet, and other stakeholders. So I think in terms of the front end, the design and manufacturing, I think we have some good plan in Saudi Arabia. And of course, we are looking for the collaboration with the whole ecosystem, Aramco, STC, and other important stakeholders.
Thank you, Dr. Said. I just want to ask you something, another question. Briefly, please, because you mentioned there is a startup companies. So is there any special program in KACST for semiconductor startups? Can you elaborate on that, please?
I think in terms of the startups, I think many programs, I think, in KACST and KAUST, I believe, and maybe Dr. Ian will shed light on some of great activities happening in KAUST. But of course, we are now in the garage, is the largest incubator and accelerator in the kingdom. They have more than 200 companies from more than 55 countries. And we just launched last year the Ignition, which is the incubator, sub-incubator under the garage, to promote the startups on semiconductors. The target is to have 10 startup companies dedicated on semiconductors. And the good things about the garage, they have full access. All the companies, they have full access to 100 labs at KACST. So we are working with some companies here. Dr. Makarim Hussein, I think, is there, and he moved, or he soft landed. He moved from the Silicon Valley to the garage, and we are working with him in our clean room to start some of part of the production. So yes, there are lots of activities happening at KACST, but of course we need to expand this, and through our collaboration with all the stakeholders in the RDI ecosystem, I'm sure we can achieve the targets.
Thank you, Dr. Said. And I think there is the Ignition website is already launched. So if anyone interested to be funded, to go there and apply. So I will thank you, Dr. Said, again. I will go to Mr. Abdulaziz. Mr. Abdulaziz, thank you for coming. I have a question. So what do you think Aramco plan in investing in semiconductor field? And how do you think the AI can be connected to the semiconductors and your investment especially?
Okay, thank you for this question, and thank you for KACST for hosting and organizing this event. Excellent question. And coming from the energy, now we are an energy company. We have recognized already as Aramco the strategic importance of the semiconductors and the smart devices. And we look at them as the backbone of the modern technologies, such as the AI.
Yes.
So from that perspective, we already are executing plans of exploring investment in global promising startups through our venture capital arms, whether it's Wa'id or Aramco Ventures. And we have already invested in this area, and we will continue to do so. This is one side, and the other side is we have also established strong partnerships with the major and leading companies in the world in the semiconductor area. You might have already heard about our collaboration with Qualcomm. And from that perspective, we plan to work together to develop solutions on device. Just imagine embedding the solutions like our MetaBrain, a large language model, or LLM for short, into devices in the field that could be a smart camera or any sensor in the field where it can collect and probably process data very quickly and reliably. So we plan to do that as well, but efforts that are already underway is our also attempts to localize some of the semiconductor industries in Kingdom in support of what we have seen today. And by the way, I'm very excited, not only as a Aramco representative here, but as a Saudi citizen, about the National Semiconductor Hub. This is really a great dream, and I think it's going to make our country, in a position to lead in the technology aspect in general. Going back to why we need to invest and localize, which is a challenge, is because we want to meet two advantages. The first one is we get an early access into the technology itself, which gives us, as a company in the market, a competitive edge. And the second, which is equally important, is to influence the design and the controls of these products so that we can meet our requirements in terms of, for example, cybersecurity, in terms of performance, and also in terms of integration with our existing systems. So this is important, and to that end, we have started to look into something important as well, which is the investment in our own people. Previously, we used to send our engineers and technicians to reputable places in the world to learn how to operate these devices. And now we are shifting. We don't want to be just a consumer. We want to be a technology provider. So we are learning now how to design them and to take also internship programs with the companies who do those in the world. So this is a shift in the development of the human talent that we do. So this is basically our, I would say, broad plans in Saudi Aramco and how we can influence the semiconductor beside other streams, because our digital journey has really created a huge demand on smart devices which rely on advanced semiconductors. And that's why we will continue to deepen our expertise in this field through partnerships and through investment in our people, and also in great ideas such as the hub we saw today. Thank you.
Thank you so much. Professor Ayan, I have a question for you. What do you think, from viewpoint, is the link between the academia and industry in semiconductors? And other questions, what is like KAUST offer for startups? Do you have like a special programs, or can you elaborate on that, please?
Of course. So first of all, thank you for inviting me today. It's a wonderful collaboration between KACST and KAUST, but I'm delighted to see we've got an international presence here today. The link between academia and industry is obvious. Academia is the source of ideas, of technology generation. Industry, apply that into solutions. With the revised KAUST strategy around accelerating impact, one of the clear goals is to take our fundamental scientific knowledge and translate that into applications. That's new materials, new processes, new methodologies, leading to new devices and new companies. The important thing for KAUST is that we retain our capability to create those ideas and then deliver them in a productive way for solutions. If you look at the foundations for KAUST, energy, water, environment, sustainability links very well with the current demands in the world to provide low energy, effective, sustainable solutions. And any solution driven by the advance of semiconductors has to be done in the light of decreasing power, using more data better, and creating devices that are going to improve life and quality, as well as bringing jobs and prosperity to the kingdom. So the role of academia is to link industry, talent, ideas, and the economy in the way that builds supply chains and industries of the future. So I think it's very clear. Now, how we do that at KAUST is a balance, as you may well be aware, between having our educational programs. We are a postgraduate university specializing in R&D through science and technology. But alongside that, having an innovation ecosystem. So we have our own technology park. We have a campus of approximately 60 startup companies. We've funded that to the tune of almost $120 million, including $80 million from external sources. And we also run entrepreneur programs alongside that to train future entrepreneurs on how to run businesses. And it's more important and more important that businesses here that are entrepreneurial understand how to scale to the market. So what we're trying to concentrate on is building a workforce that's technically capable and can establish their own high-tech industry. And so doing that in the campus at KAUST, again, gives them access to the infrastructure, again, we talked about at KACST. We also have similar infrastructure at KAUST, but we can also access our professors and our talent to allow those businesses to exploit new ideas in an environment where you can then test them. So the beauty of KAUST as a city is that we have a test bed so we can deploy prototypes and understand how they work in the real world. So we can take it truly from benchtop and apply it in a setting where it can be used to determine how the products or services should be refined. So a holistic approach to go from idea generation to products and services.
Thank you so much. So go to Professor Muhammad. I have a longer question. I wrote it down, actually. So from your viewpoint as a leading educator and researcher with many accolades, can you comment how you see the kingdom investing in terms of research and development, especially in semiconductors? And could you elaborate on the challenges and the opportunities?
So thank you very much for your question. First, I express my thanks and appreciation to His Excellency, the President of KACST, and many colleagues who were kind and generous to us during our extensive tour yesterday of the KACST facilities. So thank you very much. To come back to your question, I've gone and looked at the Vision 2030 program of Saudi Arabia, and I would like to use this and also the vision of KACST to explain my answer. The Vision 2030 program encompasses 4 main sectors: energy, industry, mining, and logistics, all of which rely heavily on semiconductors. Further, these strategic sectors closely align with KACST vision, underlining the significance of semiconductor localization both in Saudi Arabia and also in the wider Middle East region. Now, as an educator and a researcher, what I hope to do is to describe 4 opportunities and 3 challenges in the specific questions that you've asked me in helping to grow the semiconductor landscape in Saudi Arabia. So the opportunity number 1 is related to the growing international demand. So the global demand for semiconductors and semiconductor devices is continuously expanding, and is expanding at an ever-increasing rate. And this is primarily driven by advancements in technologies such as artificial intelligence, Internet of Things, 5G networks, and beyond. Saudi Arabia has a very ambitious Vision 2030 plan, and this plan focuses on diversifying its economy in these 4 sectors I mentioned too. And we can tap into the growing international demand by growing the semiconductor landscape in Saudi Arabia. The second opportunity is related to investment potential, and we've heard a lot about it from some of the speakers this afternoon. The kingdom, with its substantial financial resources, has been actively investing in technology and innovation in the past several years in research and development infrastructure and in targeted partnerships between academia and industry. So with these investments, I firmly believe that Saudi Arabia can position itself as a significant player in the global semiconductor market. The third opportunity is related to local market development. This is growing your local economy in the semiconductor area. So as the demand for semiconductors and semiconductor devices rises within Saudi Arabia and the wider Middle East region, establishing a semiconductor industry here can reduce your reliance on imports, and furthermore, it can create a self-sustaining ecosystem for technological advancement and innovation, two areas that are critical for the future growth of Saudi Arabia. The fourth opportunity is related to investing in emerging technologies. I think you need to create niche that separates yourself from some of the global leaders in the semiconductor industry. And I think one of the areas that Saudi Arabia can focus in is in emerging semiconductor technologies such as compound semiconductors. And you've already started this with your extensive clean room here at KACST. These compound semiconductors offer superior performance in various applications, including telecommunications, renewable energy, and healthcare, all areas that are vital to the future of Saudi Arabia. Now, with opportunities come challenges, and with challenges come further opportunities. So what I would like to do next is to describe three challenges. The first challenge is related to infrastructure. Growing a semiconductor industry requires substantial infrastructure investments, including fabrication and design facilities, skilled labor, and supply chain networks. While the kingdom is making rapid progress in developing its semiconductor technology sector, I believe that further investment in targeted growth in semiconductor industry is required for it to become competitive globally. The second challenge is related to intellectual properties. I think it's vital that you create, you protect, and you exploit your IP so that you can grow your semiconductor industry, and very importantly, you can use the IP to foster innovation that further drives economic benefits. The third challenge is something that we often overlooked, even though it has been talked about quite a bit this morning and this afternoon. It's related to talent development. Now, talent development and retention, I think we not only need to develop the talent, but we also need to retain the talent. It's a core, pivotal, but often underestimated aspect of the future of semiconductors. For me, it's vital that comprehensive measures, so not one-off measures, but really comprehensive measures, be put in place for the visionary education and development of talent. This entails a multifaceted approach encompassing fundamental, applied, and very importantly, entrepreneurial education. So three aspects. And I think the entrepreneurial aspect is something that is missing in most educational institutions. Across various educational levels, starting from the high schools, and I was very happy to see that you had high school students here this morning, going all the way to professional learning institutions. Talent development should focus on the challenge of educating individuals, not only for jobs today, but very importantly for future job roles that may not even exist today. So it's really important that we create talent with the appropriate skills for the future. So in conclusion, while Saudi Arabia will face challenges in expanding its semiconductor industry, it also has significant opportunities to capitalize on the growing international demand for semiconductors while it advances its semiconductor capabilities. Strategic investments, partnerships, and a focus in developing a skilled and talented workforce will be essential for the kingdom to realize its potential in growing its semiconductor landscape. From what I've heard this morning, and from what I've heard this afternoon, and from what I've heard from the panel members, I think Saudi Arabia has a great, bright future in this area. Thank you very much for your question.
Thank you, Professor Mohammed. Thank you, Professor Mohammed. So my last question to Mr. Snan. So as a CEO of Ajlan Brothers and holding Semiconductors, so I have a question. In which area do you think, or your future plan, you're going to invest in which value chain of semiconductors? Because we're starting from design, manufacturing, and packaging. So what is your plan?
Okay, thanks. Great question. So, yes, I think from my presentation, it may have sounded like we want to invest in everything.
Yes.
But yeah, I can see why that could be very confusing. So I think the good thing about the different parts of the value chain is they do not all require the same amount of investment. So what you need to invest in a design center, for instance, in the kind of startups which Dr. Naveed talked about, these are relatively small investments because we are starting small. So that investment can be done, and think of it as a long-term bet using small investments. If you talk about advanced packaging or packaging, those are now a little bit more expensive. They cost somewhere around $300 million to $1 billion. So those, I think, are something which, and again, as Ajlan Brothers over the years, we are willing to make the big investments needed in the kingdom. So I think definitely advanced packaging and testing is an area of interest. But really the big prize is in the wafer fabs. Those are the investments which can range anywhere from $1 billion to $5 billion to 15 to a $30 billion fab. So that's the scale of investment needed. And clearly when we talk about that level of investment, right, and we are prepared. By the way, we are collaborating with the key entities. We are under NDA, but we have MOUs with some of them, some large players in the kingdom, to make those investments. So I think there's no lack of willingness from our side to make those investments. We are ready and proud to do that. What is really, I think, a challenge so far is to make these investments. If you look at governments around the world, right, and let there be no mistake, we live in a global economy. When I talk to an established company in the world, in one of the top semiconductor companies, I ask them, come to Saudi Arabia. The question they will ask is, okay, if I'm going to partner with you, are you going to do at least as much as what others are doing? And I think that's where that's where we need to be competitive globally. So if they see, for instance, Malaysia or India or Japan or US is offering more attractions, we are competing with them. I'm not competing with the entities in the kingdom. We are competing with them to attract the right players in the kingdom. And I think that's where I'm focusing on investing, and that's where we have been working with the ministries. And I think I'm happy to say, I think in this country, we have the infrastructure, from an incentive perspective, the departments understand the value. So we have the policy for incentives. I think that's the good part. That's where we are doing well. Where we are, I think, the challenge is in terms of benchmarking, what we are doing with the rest of the world. And I have some credentials here, which I'll brag about a little bit. I've been in the industry for 36 years. I have talked to governments in 6 countries requesting incentives. So I have plenty of experience. You could call me a professional beggar. So with that experience, I think I know what it takes in terms of government incentives. So we have the incentive structure. I think the benchmarking piece is the second step, which we need to collaborate on. And the last piece, which is important, is the streamlining of the process. I think India is a poorer country, for instance, than Saudi Arabia, but they invested in the last month, they invested $13 billion, and they approved it in 2 weeks. So that's the streamlining piece. So you need 3 things. You need the incentive structure, you need the benchmarking, and you need the streamlining. Once we have all those 3, then you will find business houses, not just Ajlan, but many others in the kingdom, step forward and really make the Vision 2030 a reality in this country. And I think we are there. I think we have the right people. I think from my experience in the kingdom, I see we have the right focus, very smart people, which are second to none in the world, who are working in this industry. So I think I'm confident we will get there. And I think the investment areas, just to answer your question, is I think design investment can be done pretty easily. It's the manufacturing investments, which are big ticket items, and that's what we need to focus on, and which will require a lot of thought, because it's something which, which we cannot spend. These are wise. We have to spend wisely our resources. So that's something we have to discuss as a team.
Thank you so much.
Shukran.
I hope you're successful in your plan. So I think we are out of time. Everybody is just telling me the clock. So the panel discussion is finished. Thank you so much. Thank you for coming here. And I think we have Dr. Saeed, the lunch break right now. Okay, thank you all.
Ladies and gentlemen, we will now have a lunch break and exhibition at Building 17. Golf carts are provided outside for transportation. We wish you a pleasant time, and we will see you back in 1 hour.
Assalamu alaikum wa rahmatullah. Thank you for joining us today. Welcome this afternoon, in this afternoon's session, Pioneering Semiconductor Excellence in the Kingdom. In this session, we'll be discussing how can the Kingdom become a major player in the semiconductor industry through its startup ecosystem. We're fortunate to have a distinguished panel of experts from various parts of the ecosystem, semiconductor ecosystem, to give us an insights into the Kingdom's startup ecosystem, as well as providing us advice and thoughts on how the Kingdom should proceed in advancing its semiconductor. Electronic design and automation will power the startup ecosystem in Saudi Arabia. Thank you.
Good afternoon, everybody. Welcome back from lunch. Thank you to the Kingdom for inviting us, Siemens, especially Siemens Semiconductors, Siemens EDA, to talk about the future of semiconductors here today. Okay. Is this better? Okay. So as introduced, I'm the General Manager and Vice President of Siemens. I want to take you through a few minutes of Siemens overview. So you might think of Siemens as really good at building trains or thermostats in your home, but we are actually a technology company. And as a technology company, we look at different segments of the industry. You can see infrastructure, mobility, healthcare. All these segments present problems which can be solved very efficiently through digital transformation. And that is how we are a technology company. We are taking the world through a digital transformation. And at the heart of this digital transformation lies semiconductors, which is the topic of this entire forum. And semiconductors, you may think of it as a physical device, which it is, but that's the tail end of the journey. The front end of the journey is entirely a digital spec. It's the vision of the designer. So we like to present this idea of designing a semiconductor as a digital twin of your vision, which is based on a variety of tools, and that's where Siemens EDA comes in. And you can see that the software that you use to design these extremely complex semiconductors span a wide variety of stages. At the very top, you can see that today the industry uses various platforms: digital design platform, verification platform, analog design platform, verification platform. And the whole process can take anywhere from 1 to 3 years, depending upon the talent of the team and the infrastructure. Even the compute that all of this software is running on can determine your speed of execution. We like to think of ourselves as experts in this space, having been in this business for over 4 decades. One key point that I want to make for the Kingdom is, if you look at the very last line, the most labor-intensive, but also the highest ROI component of this process is the design phase. This is where the talent that is going into semiconductor design will innovate. They'll create solutions to a variety of problems. And this morning you had excellent speakers from even high schools, award winners, and what they did is essentially focused on this left-hand side, where they innovated to create new designs to solve novel problems. The second piece, which is the hardening of the semiconductor design, the digital twin element, to take it from a virtual spec to an actual design that you can then manufacture, that can be outsourced. And many of the speakers in the morning were describing Epic Systems, for instance, is a company that has been built so that it can manage this whole process for you. And at the very far end is the infrastructure building, and as other speakers have mentioned today, that is high effort. So our thesis throughout the presentation is that the kingdom can really benefit by focusing on the design element, and specifically within the design element, we are also proposing an power as a key element to design efficient semiconductors. And you'll see that as I walk you through the talk. Now, the industry as a whole, and some people have mentioned this, it's not just up and to the right, so please be mindful that there are swings, but this has been the historic nature of the semiconductor industry. It's a $550 billion industry, and it has had multiple swings over decades, but there's always a recovery. And the most recent recovery highlighted on the very right, you can see that it's a sort of steep U-shaped recovery, and that's where we are today. So the industry is always growing up and to the right, but there are some changes here and there. I should mention over here that in EDA, we keep investing throughout these down cycles. So the role in a changing world can be understood by looking at the changes that the world is going through, from unprecedented supply chain disruptions like we discussed in the morning, to trade wars. And these are inflection points in the industry. Like the trade war has now created a lot of localization of the semiconductor supply chain. AI, another inflection point in the industry. We did talk about multiple types of designs this morning. Today, the attention is all on AI. And it's not just a question of designing more AI chips, it's also how do we design these sustainably. Sustainability is an extremely important aspect. Mr. Ross talked about wet. And that's, if you can manage it correctly, that's one way to do sustainable design. But managing it correctly is not straightforward. So behind all of this is a thoughtful ecosystem that has to be deployed to get to the designs. I'm from the Silicon Valley, and in the Silicon Valley, Mark Andreessen famously said that software is eating the world. This was, 10 years, 12 years ago, something like that, and how true it has become. But hardware is where this software runs. So this AI example that I was giving you, to run these AI models, you need a lot of hardware. And data is driving it, and I'll show you a few examples. Overall, the industry, the systems industry, these AIs going into data centers, that's what we call a system. That's a significant industry heading towards 3.4 trillion, and semiconductor is a growing share of that systems industry. So it's becoming even more important as time goes by in pretty much all vertical markets. And look at the expected data trend. This is where we are. You can hardly see that bar chart in 2024. So this is going to be an exponential rise in data between now and 2030, which you can correlate to the $1 trillion semiconductor industry projections that you see in various reports. Managing all of this data requires tools, requires hardware emulation, a lot of what EDA companies can support you with. So society in general is demanding that as the semiconductor demand goes up and the complexity explodes, we manage the downsides. And this is the dilemma today that the overall world has, that there are challenges associated with semiconductor design. Cost and schedules are skyrocketing. Universities are not graduating enough students. We've talked about that this morning. I'll give you an example. In the United States, only 3% of the graduating class focuses on electrical engineering, or what we call the EECS major, EECS major. In contrast, there are other countries such as India, Egypt, where it's more of a 50-50 split. So focusing on talent creation is extremely important, and the existing talent is aging. So there is this sense of urgency in the overall industry. Now, the investments that we are talking about over here with the kingdom have been recognized. The need for this investment has been recognized the world over. And you can see large amounts of money is being spent by existing semiconductor leaders as well as upcoming semiconductor leaders. So indeed, it's a great decision on the kingdom's part to enter this market and invest heavily. Now, the investment is not just in manufacturing. As I mentioned, design is a significant component, and design is often thought of as R&D in semiconductor terms. And this R&D has had some down cycles over the last few decades, but for the most part, it is up and to the right. Especially in the last 7 years, there is absolutely no stopping the R&D investment that's going into semiconductor design the world over. So this is really a great time to start investing in this field, in the talent, in the R&D that is required to get ahead and make a difference in the economy. I can go on and on, but we would like to propose that if you haven't read this book, The Chip War, please stop by, meet one of my colleagues. This is the book by Chris Miller. It says, Chip War, the fight for the world's most critical technology, and how true it is. Chris Miller started researching this back in 2014, a decade ago, and today we are seeing that this has become a very critical technology. My colleague here, Dennis, has additional copies. If you're interested, please do come talk to us. Now I'll spend a few minutes on connecting all of this back to Siemens EDA. I mentioned design, I mentioned manufacturing. If you go one step lower, there is an IP for intellectual property design, and then there is the product manufacturing. So we propose that the kingdom can also focus on some power-efficient IP of their own. Here is a chart that explains the whole process. We, having spent over 4 decades, would like to offer our services in bringing your talent and your companies, startup companies, into this design very efficiently as a bridge. On the top, on the right-hand side, you can see a bridge. And having come from Silicon Valley, I'd like to propose that think of this as a Golden Gate Bridge, which is connecting design to factory, and you can leverage products such as Calibre and Tessent from Siemens EDA. I run the Tessent group within Siemens EDA as a highly reliable industry standard product so that your designs are done right and have high yield. Yield is a significant concept, which is good parts. And just to conclude, we have a long legacy of providing high quality Siemens EDA software to the entire industry. You can see 98% of the top 50 semiconductors uses us. So specifically for the opportunity to the kingdom, we created a 2-minute video. I hope you enjoy this, and I hope your takeaway is that there are multiple ways you can get into the semiconductor industry, but we are submitting that please consider optimizing power, because that's a key concern for sustainability as you look at your entry into the semiconductor design. With that, thank you.
Thank you, Anko, for giving us an overview of the semiconductor space and highlighting the important challenge of power consumption. Our next speaker today is Dr. Ahmed Al-Fayfi, Director of Saudi Semiconductor Program. Thank you.
Thank you all for coming today. So, my talk today, it's about the Saudi Semiconductors program, and so it's what we are doing towards building a semiconductor industry. So what do we need exactly? So there are several things that we have to have in order to build or successfully build an industry. So why shall we focus on many elements? So KACST, as King Abdulaziz City for Science and Technology, 2 years ago decided that it will launch the Saudi Semiconductors program to just focus on one thing, which is the talents. So why the talents? It's because KACST has the infrastructure, it has the researchers that were developed in top schools, and they want to expand their knowledge to the next generation of scientists and researchers here in Saudi Arabia. So, so this is out of flip. Yeah. Oh, okay. So here what I'm doing is it's that chicken and egg paradox, but I'm trying to make it look a little bit scientific. So why don't we have an industry? Why don't we have the talent? So the main reason is we don't have, there are a few design companies that are here in Saudi Arabia right now. And that's coming because there are no talents. Talents, when you go to the universities and you ask the students, why don't you focus on our major in electronics? They say there is no industry. Why shall I go to this track? Other tracks are, there are already players there in the market which can, employ me. So in turn, less courses are provided by universities. So this created no industry, no pipeline problem for Saudi Arabia. That's why KACST created the Saudi Semiconductors program 2 years ago, and to just try to build the next generation of talent, both in design and manufacturing. So what are we doing in the Saudi Semiconductors program? Our focus is to build the talent, but how are we going to do it? It's through providing training and tools and resources for the IC designs and the prototyping area. So this is similar to what other countries and programs are doing worldwide. For example, CMC in Canada or your practice in Europe. But with one difference, here universities, like most of them, they do not have access to the design tools. So we'll have to try to find a way to provide these tools to them. And also the level of exposure of students to the field and to the value chain and how the design tools, what's the flow in this industry, it's not 100% known. I know some of the universities, for example, KAUST is working in this direction, but not all of them. So this created a bit of challenge, so we decided to go in 2 or 3 milestones. First one is the training, which is kind of an awareness more than a training. It's just to grab the attention of everybody. We have these programs. If you enroll in these programs, you'll know the design flow, and then you will be able to do the prototyping with us. And after that, we can go to the next step, which is providing the tools and then building the IPs that they can utilize in their designs. So instead of trying to do everything at once, we decided to focus on 2 technologies mainly in the beginning. First one is the integrated circuits, and the other one is the MEMS. So why these 2 in particular? First, the integrated circuits, we can have access to an open source PDK, which is a challenge for most of the Saudi universities. For the MEMS, we can manufacture them in-house in our clean room. So we decided we can start with these and then move to the other areas, like, for example, FPGAs and photonics. Once we are a little bit solid in this direction, we don't want like to cause a distraction on which direction they shall follow up or like go for in terms of prototyping, education, and so on and so forth. So we created a roadmap that focuses on building capabilities in Saudi Arabia instead of relying on just the international processes. So it's first one is about building the capabilities. So our clean room is capable of reaching 800 nanometer CMOS process. So we started that one, but we didn't develop the whole process. We didn't develop the PDK. It's on our roadmap, but we needed some equipment to reach that milestone. So that's why it's on our roadmap, but we'll start on it in 2025. Right now, what we are doing is we are utilizing eFabless and their Sky 130 process, which is convenient and easy to access. So the second one is it's a MEMS process, which is a simple silicon insulator process. So this one, we just finished developing it completely in-house in our clean room and KAUST clean room. So with the launch of the National Capability Center this day, I think it highlights how important that initiative to our program, because right now we can go there to KAUST, finish the fabrication of the mask, finish some of the steps in this fabrication easily. So this process, it's also roughly, it takes 1 to 2 weeks. So that's why we wanted the process to be in-house. So the main reason that we wanted the process in-house instead of just going to the international foundries is to have full control over it. So if you start a course on MEMS design, for example, and the student finishes their designs in the, let's say, first month, and then they send it to for fabrication internationally, and then they will wait 3 to 4 months until they get their chips back. They might forget a lot of things about it, especially if we are talking about bachelor degree students. So that's why we were more interested in building it locally. So this is the process that we have developed. It's, as I mentioned, simple process. Started the process design in roughly 2 or 3 months ago. Started the process in our clean rooms. There are 4 devices that are there as a shuttle, or let's say a tentative shuttle or training shuttle for us, just to build the knowledge in the process. And then we completed the first run last week. We have 4 devices. So now that we have the process ready, what do we need to go to the next stage is to provide the tools, the design tools to the students, and to give them training on them so they can do the designs, and then the next shuttle will be more populated with designs instead of just like 4 chips. So training. As I mentioned, we're focusing more on the analog and on the integrated circuits and MEMS, plus the manufacturing. So manufacturing, it's one of our strengths at KACST. We have our clean room, so which is a unique opportunity for students and researchers to get training on the manufacturing. But it's this is just it depends on what kind of or what level you want to reach with your target audience, with the trainees. So we have 3 kind of trainees. First one is the high school students who this morning I think you saw 2 of the students who won international prizes just because they have access to the manufacturing facility. The other 3 areas, so we started also with analog. last year we had training on the analog IC design flow, and I'll talk about it in a few minutes. And then next year we plan to go for the digital, and this year we'll go also for the MEMS that's on the same process that I have talked about. So if we are talking about the training programs that we have offered, so first one so we did it in like to explore or test the water. So how prepared the students to these programs? The first one, it was mainly on demand. So and we were just exploring and checking how much they are progressing in this program. We noticed that they were not, most of these students were not involved to the end, only almost 1 or 2 students who finished the whole material. So, and the other one, we made it live sessions. In this live session, we explained the whole flow and asked the students to do the design. No, you guys hear me? Okay, so we asked the students to submit their designs. Only 3 submitted their designs from more than, I think, 100. So we decided to change the delivery method. So in the PLL design program, what we did is we are having a training session and then a review session that we ask them. You'll have to deliver, like for example, you have to go through all the processes of the flow. This week, we'll review the flow with you, give us your design, we'll check the schematic, and then help you in a Slack channel that we created for this purpose. And then for roughly 10 weeks, we finished the whole program. This one had much better success. We finished with roughly 7 designs. And then we moved to the manufacturing, where some of the students, I think they are finishing this week, a 2 months training. It was very intensive, like from 9 to 3. So right now, we are trying to combine both. So especially if it's in the design, especially for the MEMS, if you submit a design, you'll get the opportunity to go and fabricate it in the clean room. This will give them like a better motivation to finish their designs and like get the learning much better. So this was the graduation of the first batch of students. They were graduated by His Excellency Engineer Suwahala last year. 40 of them were honored with certificates by His Excellency. So last thing, it's about the tools. I think it's one of the challenges that Saudi academia are facing, like the access to the tools, it's quite difficult. So what we tried, like several paths. What we did in the trainings, we started with the open source tool, but what we found, most of the students were not familiar with Linux. Most of them, it was difficult for them to follow up on the open source tools. I think they were a little bit difficult. So that's why we are switching gear right now to different tools. But at the same time, we wanted everybody to have access to it. So, and also at the same time, we wanted to provide the prototyping area for researchers and students. So right now, if you go to the SSP website, you will find, if you log in, you can find a list of processes that we provide through eFabless, 130 nanometer processes that you can apply and like prototype your chips for free. Either in tiny tip-out, which is 160 microns by 100 microns, or in chip-ignite shuttle, which is roughly 10 millimeters of area. So yeah, this is the prototyping process. You go to the website, you book your area for free, you get the design tools from there for free, and then you submit the layout to us. We take it all the way through the fabrication and then send it back to you. So actually, we had started that one. We are supposed to receive we did it in 65 nanometer, but it was a different process with through TCMC in collaboration with KACST researcher. But yeah, we have received 2 chips through this process. So right now you can have access to anybody from the Saudi universities, researcher or students. They can have access to KAVANTOR right now. It's up there in the cloud. You can just apply for the license and you'll get access right away, and then you can start using the software immediately. The second one, it's in collaboration with, it's still on process or in process with our friends from Siemens and CDT. So we are now in the final stages of getting the tools and then having them also on the cloud. So the student will have, like the design on his machine or on her machine, and then access the license in the cloud to design the chip. And we will also provide them the training so they will get familiar with these tools. So in summer we'll start just after the holidays. We'll start 2 training programs, one in KAVANTOR and the other one on IC, just to design an OPAM. It should be announced very soon. And yeah, that's mostly what we have done so far. We are planning to, what we are doing here shall feed the National Semiconductor Hub that was announced this morning. We are trying to just create the pipeline of talent that can feed to that advanced training program, and then from the training program right to the industry. So yeah, thank you so much.
Thank you, Dr. Ahmed. Now I'd like to call our panelists to the stage to discuss. We're going to be discussing Saudi startup ecosystem with regards to semiconductors. I'd like to call Dr. Makarim Hussain, founder of Luxnor Technologies, which is a startup, semiconductor startup here at the garage. I'd also like to call Dr. Shafi Touhi, CEO of Epic Semi and founder of multiple startups in the semiconductor space. I'd also like to call Mr. Omar Al-Shaban, who's a champion of startups and CEO of the garage. And I'd like to also call Abdurrahman Al-Aql, Dr. Abdurrahman Al-Aql, who is the general manager of the Cybersecurity Institute at KACST. Hello, can you guys hear me? Can you guys hear me? Yes, I'd like to encourage, I'll be asking questions to our panelists, but I'd like to also encourage the audience to ask questions. We really welcome any interjections from the audience. Maybe I can start with Omar, and can you, you're a champion of startups here in the kingdom. Can you tell us about some of the initiatives that maybe in the kingdom, but specifically here in the garage, you guys are doing to foster a startup ecosystems for semiconductors, please?
Assalamu alaikum. First of all, it's a pleasure to be among an esteemed panel, and it's a pleasure to be with you all. And welcome to the garage. So many efforts. I want to start by looking at the startup ecosystem at large. When you look at the startup ecosystem, we obviously look at a holistic approach where academia comes together with regulation, comes together with the funding, and with the startups and talent, and also access to market and access to opportunities. And the beauty about what's happening in the startup ecosystem here in the kingdom, that this ecosystem is working all together as a cohesive force rather than working in silos. And I'll give an example. So we're here in the garage today, which is a product of collaboration between MCIT, KACST, the Saudi Federation for Cybersecurity. But we don't work alone. We do work with the likes of NDTP, the National Technology Development Program, which unlocks many opportunities for startups and also for service providers in order to create entrepreneurial programs that are helpful for the ecosystem, such as VC-backed incubators and accelerators, subsidizing some of the salaries of the founders, creating attractive programs to attract deep tech startups, and semiconductors being in the heart of that as well as working with other ecosystem partners like the Saudi Venture Capital Company, for example, or even some NGOs and NPOs like Endeavor or the Saudi Venture Capital and Private Equity Association or so. So when the ecosystem works together, this results in numbers. And the numbers were very evident last year, where Saudi Arabia became the #1 most VC deployment of VC money in the region, in the MENA region, with around $1.4 billion US. And this number, inshallah, will continue to increase in the coming years. So enablers are across these sectors. So when we talk about infrastructure, a project like the garage is very evident. When we look at regulations, and many regulations that were unlocked, whether it's sandboxes that entities did, like the Central Bank and SAMA for fintech, for example, or an initiative like this where you have a national strategy for semiconductors and for deep tech, having the access to the KACST labs for scientists and for innovators to come in and to play a role in doing this. All of these regulation, access to market, access to funding, whether it's smart funding like new instruments like venture debt, or even fostering the VC scene, this all come together to create a very thriving ecosystem, which we are witnessing here in the kingdom.
Thank you. Dr. Makarim, you're a founder of Luxnor Technologies. It's a startup here in the garage, right? Can you tell us what really attracted you to start here specifically, in the kingdom in general? What attracted you to do these?
First of all, Luxnor is actually registered in Oregon. So
Okay.
we started in Oregon. And we moved to the garage last year. And the common theme is what you have heard all morning today, which basically the leadership would look out, would give some incentives, would invite candidates, and that's what happened. KACST invited me to come over, and for what I do, I need a microfabrication facility. That's very critical. So KACST was offering me microfabrication facility and a nice place like the garage, which is a very inspiring place. So with these two, Luxnor came in with unique IP and a methodology to contribute at the intersection of display and semiconductors.
Thank you. Maybe I should switch to Dr. Shafi. You started several companies in this space. We have a lot of young researchers here that maybe one day they want to do their startup or are planning to do that. What advice do you have for someone doing a startup space?
I think in general, number one, you really have to think about it is really, are you solving a real problem that the people will care about it or not? Usually there is a tendency, you fall in love with your idea, and we all know that love is blind, and are you really solving the problem or not? So you really have to think hard, are you solving a problem or not? The second one is the focus. You really need to have a North Star that you focus on. You're going to get distracted by a lot of shiny objects, but you really have to have a North Star to really shoot for and get focus on. The second one is really also very important is hiring. You try to hire actually smarter people than you. Every time you surround yourself by smart people, you're gonna benefit from it. So make sure that you hire smarter people than you. There's nothing wrong with having a guy in your team that's actually smarter than you. The more important thing is also for hiring. There is a rule called actually hire slow, fire fast, which means essentially that take your time to hire the right people, but when you discover there is a person that does not fit, fire very fast. because there is a tendency for everybody to delay the firing for another 3 months, 4 months, and that's not usually good for anybody. The last advice, don't run out of money, because if you run out of money, now you are under the mercy of the VCs, and you're going to get bad valuation and so on. This will be my advice to anybody who really want to start a company.
Thank you for this practical advice. Maybe I go to Dr. Abdulrahman Al-Aql. Maybe can you tell us a bit about, now we're launching startups in the kingdom, and we're launching an ecosystem. We're going to have to collaborate with people from around the world. Can you tell us what are the challenges, in terms of cybersecurity in this area of in semiconductor supply chain? Yes.
Right. So in order for us to understand the semiconductor industry, we have to know the capabilities here in the kingdom. And one of the clear things that we understand today is we are not able to manufacture chips today as of yet. We are aiming at having this capability built, but right now we do not have this as an available technology. So we have to resort to partners that are external. And this is a common practice. Even Apple, which is a big company, does not manufacture their own chips. They design their own chips, but then they outsource the manufacturing part to a partner in another country. So here's the bad news. When you deal with third-party partners, they are not always trustworthy. You are sending your designs, you are sending your assets, and when you do that, you actually expose your secrets, your recipe, to a lot of people that might not be as honest or as honorable. So you get a lot of problems with your designs. Some things can be modified. Your design could be reverse engineered, or something can be overproduced, and then your technology can be sold without your knowledge. All of these problems and risks happen today, and they are actually real challenges that everybody that designs chips deal with. So how can we actually be part of an ecosystem that we do not 100% own? That's a really big challenge, and almost every chip designer faces today.
Thank you. So I'd like to encourage the audience also to ask questions if they have. Maybe if I heard you mentioned design, and I heard this quite a lot, that people saying Saudi Arabia should focus on design. Maybe I can ask Dr. Shafi, which area of design, and design is a big field, which area of design you think the kingdom should focus on? And maybe if you have advice to people who are doing this, who want to start a company in this area, what?
Yeah, currently, actually, what we are seeing in the industry, I can see there is probably 3 transformation happening right now. One of them, most of them actually not a technology breakthrough, but it's really created because of either geopolitical situation, or because of the cost, or because of the end of what we call Moore's law. For example, because of the geopolitical situation, a lot of people now are moving into the direction of having an open software, and hardware. We have seen that already in the RISC-V, for example. It's a processor that will be competing with both Intel and ARM, for example. And it's an open spec. There is no IP involved in it, and if you get the spec and you are smart, you can design your own processors from that point of view. And you are not subject to any other IP or any restriction that anybody can do it for you. So that is one example that you could actually take advantage of it. The second example we are seeing, just recently, we are all familiar with GPU and the restriction that happened in the GPU. What we are finding, a lot of people now is moving into the direction of what we call the custom silicon. So instead of relying on one chip or one design fits all, the people go and design their own chip, that is really fulfill the function that they need. There is no reason for us to have a GPU that does everything if your application only will be, for example, at IoT. You don't need to do that. It's just too expensive, power is too high, you could put a restriction in yourself. So we're seeing a lot of demand now for actually custom silicon. It got magnified actually because of the restriction you get from NVIDIA. You are seeing now, for example, software company or high-tech company like Google and Microsoft and AWS, they are all now going and designing their own chip because they know how to optimize it from the power point of view, from the performance point of view, and from the cost point of view. And that trend will continue, and I think this is the direction that everybody is moving to.
Thank you. Omar, if I may ask, I understand there's an initiative that was launched a few months ago called Ignition, and it's specifically an accelerator for semiconductor space. How different, in your view, should we? What's the difference between nurturing a startup in other fields versus nurturing a startup in the semiconductor space?
Look, it's quite similar. So basically, they go through the same program as any incubator or accelerator in that regard. The most important part is that we look at creating a community. So semiconductor, I'm not going to claim that I'm a semiconductor expert. However, any industry today has multiple facets and multiple elements to it. And we try to look at complementary startups that can come together in manufacturing, in design, and technology that would allow sales, etc. And this helps creating that community that would be cultivated by such an initiative, but it will be ever growing. So the root program is very similar, which is access to the labs, access to mentors, access to shared services, equipping them with, you can appreciate many of these startups there might be researchers and scientists, but not entrepreneurs. So how can we skill them to think more of entrepreneurs? But in essence, it's like any other industry with a laser focus on how this industry at large could be changed. And His Excellency mentioned today during the opening the clean room, the facilities that are there. So we give access to all of this, which is I think it's a very unprecedented program globally when it comes to a very specific sector like semiconductors. So it's quite exciting, and we really hope to see the benefits of that program very soon, inshallah.
Thank you. Dr. Makarim, you're now, you're founder of a startup, and can you maybe give us advice on what do you think is the most critical aspect of launching a startup in the semiconductor space? What is the most critical aspect that founders should focus on?
I will answer this in the context of Saudi Arabia. How about that? So I believe, I was one of the first companies to start up in that field in Saudi Arabia. From that perspective, we are blazing the trail, if you wish. So the ecosystem is forming, and my expectations were actually very moderate in that regard, because with the ecosystem forming and nothing settled yet, there are problems and there are a lot of learning. And maybe the biggest obstacle for me is funding. Most of the venture funding in Saudi Arabia is geared towards software and other non-hardware ventures. So this is one of the key things. If we are starting a semiconductor industry in any other field other than the design, we need also the ecosystem to come up and support by ventures, by investing in these companies. So venture is one problem, as far as supporting in clean room, supporting with the staff, supporting with the environment, all that is available, and I have no issues with it.
Great. Maybe I'll ask, last question to Dr. Abdulrahman Al-Aql. What do you, when we think about cybersecurity, we think about software, and I think most academic programs focus on that. What role do you see the universities in Saudi Arabia should have in cybersecurity when it comes to semiconductors?
Right. Yeah, this is a really good question. So basically, what we focus on in the research community and in the institute, in Cybersecurity Institute here in KACST, is to actually help enable startups in semiconductor industry to be able to have a successful product. And in order for us to do that is to actually develop a couple of solutions that will help securely design and manufacture chips, right? So what we do is we help designers add layers of protections that will allow them to use untrusted facilities and manufacturers. So the manufacturer will get designs that are not understandable or functional, and that helps prevent reverse engineering, modifications, and any other threats. And then when they get the product manufactured, we actually help them certify these products by reverse engineering these products here in KACST, by analyzing each layer in the chip and comparing it to the design files that we have available, because we designed the chips. So as a research community, we have developed these solutions to authenticate and certify products. So any startup in the kingdom today has access to good technologies that are not trusted today, but are advanced, for example, 7-nanometer nodes or something even lower, and still have the level of security and assurance that comes with this level of application.
Thank you. With this remark, I'd like to thank our panelists. Let's give them a hand. And I guess in 15 minutes, we'll start the next session. Thank you.
Okay, shall I start? All right. Good afternoon, everyone. My name is Gautam Chattopadhyay. I work at NASA's Jet Propulsion Laboratory. And my talk will be about NASA technologies for space exploration. So let's start. So I work at NASA JPL. Jet Propulsion Lab is on the west coast of the United States, and we have different centers all across. My talk will be slightly different from whatever you have heard so far. What I'm going to talk to you about is the science and the technology that we develop at NASA. Of course, I'll talk a little bit about the semiconductors that we are trying to use, the silicon semiconductors, because in space, 3,5 gallium arsenide indium phosphide we have been using for a long time, but there has been a lot of challenges of using silicon. How do you qualify them? Because the current generation of silicon semiconductors are not that good when they go to space. So let's start here. We are actually, JPL is very close to downtown LA. We are part of Caltech as well. And currently, if you look at all the NASA missions that we have, many of them are flying already, and some of them are, okay, let's go back, sorry. So many of them are already flying, and some of them are already in plan, like Europa Clipper mission is going to be launched sometime next year. So we have been very busy over the years. And we know that these are some of the flagship missions that we have developed at NASA. We have done Voyager 1 and 2. Many of you know that Voyager 1 and 2 has gone outside our solar system. The farthest a man-made object has gone so far. And recently we are still getting signals from Voyager 1 and 2. And then Voyager 1 currently is actually 42 light hours away. It's about 45 billion kilometers away. And it's still sending signals. So that shows when you are building something for space missions, what kind of care that you'll have to take so that it does not fail. Failure is not an option in our parlance. And we have used Magellan for Venus. For the first time, we are able to actually map out what the terrain of Venus that were not possible before. But let's talk about some failures as well. Galileo mission we had. That first time we are trying to use a deployable antenna, and that didn't open. And we did not have a high-gain antenna to send all the data back. But we have learned from there, and we have been using those technologies now for deploying antenna. But let's start with science and technology. Whatever we do at NASA is driven by science. We are trying to answer big science questions. And for that, we are trying to develop the instruments and develop the technologies and finding out what are the technology gaps we have. So that's where we actually invest in our technology funds. So let's start with the Big Bang theory. This is not the Big Bang theory you watch on TV. This is the real Big Bang theory. The first light of this universe actually came out in 400,000 years after Big Bang. Whatever you are doing electromagnetics, we cannot go back in time before 400,000 years in electromagnetics. However, what we can learn is go back in time and see how stars and galaxies are formed. And that's where the excitement is. So this is the origin. One of the biggest questions that we are actually trying to answer currently is, are we alone in this universe? Is there life outside our planet Earth? So this is the biggest science question that we are trying to answer. And if you ask me, could there be life outside our planet Earth? First of all, I want to make very clear that we have not found any form of life anywhere outside our planet Earth, not even a single cell. Whatever you see on YouTube or internet, if you see aliens, don't believe them. If someone has seen any aliens, please ask them to talk to us so that we'll stop investigating all this matter and stop spending billions of dollars. But if you think about it, so what is the probability of having life somewhere else? In our Milky Way galaxy, we have about 100 billion stars, order of magnitude. And in our universe, we have about 100 billion galaxies. And we are finding that most of these stars in our universe has planets, and multiple planets, more than one planets. The question is, what is the probability that we find one such planet out there where conditions are such that life could exist? That probability is non-zero, and that's why actually we are spending our time and effort to find such a planet and find if there is life. I'll talk a little bit about some of the technology that we are developing for that, and we actually found many of these exoplanets. So far, about 5,100 such exoplanets, planets outside our solar system. And many of them are in the habitable zone that they can actually hold life. And we are trying to find out, is there life there? It's not an easy problem to solve, but we are getting there. So if we look at that, I said there could be trillions of planets out there, but how come we only found 5,000 only? The reason is our technologies are not good enough. We have looked at in our very narrow area of our Milky Way galaxy. That's why we found only 5,000 such planets so far. So I need your help to come and work with us, develop the new technologies so that we can actually see further and find those planets. So the question becomes that those are far off places, these planets. Is there possibility of life our own solar system? Answer is yes. Look at this. This is Enceladus. Enceladus is the moon of Saturn. What you are seeing here, water gushing out. This was actually detected for the first time using Herschel Hi-Fi observatory, the instrument that actually I was involved in developing. We found this is a very cold planetary body and all ice. However, if there is water coming out, it has to have source of energy. If there is a source of energy, if there is water, can there be life? When we are talking about life, we are talking about our kind of life, hydrocarbon-based life. And for that, we need water to exist. What else is coming out? We don't know. That's why NASA is planning a mission to go there and find out what are the things that is coming out from this planetary body. Another very interesting body is Europa. Europa is a moon of Jupiter, and scientists believe there is a water ocean underneath thick ice shell of Europa. If there is a water ocean, which means there has to be a source of energy. We don't know. Suppose NASA is actually going to go to Europa. If NASA had come to you, or Saudi Space Agency comes to you and asks you what kind of instrument you are going to build to find out if there is life in that water. Obvious answer is you send a drill a hole, lower a bucket, and see if there is any fish, right? Unfortunately, for these missions, it takes 7 years to go to Europa. And total amount of energy available for these missions is about 400 watts, 4 light bulbs. You cannot send a drill to an outer world to drill a hole. This thickness of this ice is about 15 kilometers to 100 kilometers. We cannot do that. So we'll have to come up with new ideas. So that's what we have actually developing technologies. So orbiter, we are sending an orbiter, and we are going to find out if there is any organic materials that is coming out of this. Another thing that we keep going back to Mars, many of you know, because Mars is our nearest neighbor, and it only takes about 7 months to go to Mars. One of the interesting things about Mars is in its early history, Mars actually resembles so much like our planet Earth. Is there life on Mars today? We don't know. Was Mars ever habitable? These are the questions we are trying to answer. And for that, we have been building all these rovers over the years, from smaller to larger. And the most recent one that we actually sent to Mars is Perseverance rover. This is the most expensive self-driving car that we can build, $2 billion. But we have 10 or more instruments, and it's doing amazing stuff. It's actually drilling hole, taking the materials out, and trying to find out, is there any sign of life on Mars? These are the pictures actually from Mars. Look at them carefully, because many of them look so much like our planet Earth. Interesting thing is we get this kind of terrain only when there is a flowing water. which means at one point of time on Mars, there is flowing water. But if you go to Mars today, we don't see flowing water. The question is, what happened? Where did that water go? Can it happen to our own planet one day? And what can we do to prevent it? So these are the big questions that we will have to answer. And water is important for life as well. So that's why water, we are actually trying to find out about waters. Do you know that when our planet Earth was formed, there's no water? And scientists believe that comets brought water to Earth. If you tell me this, we'll have to prove that, right? What do you do to prove that comets brought water to Earth? It turns out there are different kinds of water. The water that you are drinking right now is H216O. That is, oxygen has different isotopes. 16O is the most stable water. But there are other kinds of water, H217O, H218O, HDO. One hydrogen, one deuterium, one oxygen makes water, and heavy water for nuclear power plant, D2O. If you take the abundance of different kinds of water that I mentioned, it turns out the ratio of that abundance is very similar. What we have planet Earth is to different comets. If the abundance ratio is same, source has to be the same. Unfortunately, we have made only about 10 such measurements, this ratio. So statistically not significant enough. So we'll have to still make instruments, go to comets, and answer this question. So we actually, as a PI, I came up with a new instrument concept, what I call Water Hunting Advanced Terahertz Spectrometer. We have to make this instrument small. Currently, if you have an instrument of this kind, which can measure these different waters, it's like a desk like this size. And it will weigh about 25 to 30 kilograms, and it will need about 60 watts of power. We cannot do that. So what we are trying to do is build an instrument that will be 2 kilograms of, less than 2 kilograms of power, and takes less than 5 watts. How can you do that? That's where the innovation comes. Innovation does not happen that you wake up in the morning and say, let's innovate something today. Innovation happens when you are faced with a challenge and trying to actually make something, make a big difference. Look at this. As I mentioned, we are trying to measure all these different kinds of water, and all these waters have rotational vibrational frequencies associated with that 509 gigahertz HDO, 548 gigahertz, 818O, 17O, 552, and most abundant water H216O, 557 gigahertz. Very strong water line. And we'll have to build an instrument to do very high resolution spectroscopy with these, compress everything, low power and low mass. So if you look at all these block diagram, you have to build an antenna that will fit in a shoebox-sized satellite. So we decided to go with very low profile antenna. I'll show you what kind of antenna. You'll have to calibrate your system. You'll have to calibrate means how do you calibrate your system? You'll have to check with a known load. Switches are not available at this frequency. If you want to buy a switch at 557 gigahertz, low loss, does not exist. So you'll have to come up with an idea to build it. Then we are using gallium arsenide-based Schottky diode mixers here. This is a workhorse. These are all room temperature systems. And then you have to generate the signal in the terahertz frequencies as well, source. Gallium nitride you heard in the morning. Yes, gallium nitride-based semiconductor chips we are using to generate this kind of signals as well, to amplify. And then back-end spectrometer, and you need a synthesizer. That's where I'll talk a little bit about the semiconductor part of this forum. So you'll have to innovate. That is the question. So we came up with these antenna, low-profile antennas working at 550 gigahertz. You can see these are metal reflector antennas. You need RMS, about 5 to 7 micron RMS roughness. So it's extremely challenging. Then also we came up with antennas that are lens-based antennas, very low profile, 6 to 7 centimeter. If you look at antennas at these frequencies, they're big. They have, a subreflector hanging out up there. So we have to come up with solutions to build new kind of antennas. And we actually did build it, tested it in our lab, I'm not going to show much about this. And next one, as I said, you need to have a switch, low loss switch. It's called DQ switch, so that you can compare with an existing load. Like every time you measure in your lab vector network analyzer, you calibrate your vector network analyzer. Here, we actually build a MEMS-based switch working at 557 gigahertz. So there is a video here. You can see there are metal waveguides. This one is a metal waveguide. The dimension of this waveguide is 200 micron by 400 micron. This is a metal structure. The thickness of your hair is about 150 micron. So we are cutting metal with a piece of hair. So these are the challenges that you have to overcome. But the MEMS does is actually makes it very low mass and low power system with a very low loss. That works very well. And also we made, using a piezo motor kind of low loss switch here, you can see. These are waveguide again. That is moving from one waveguide to the other. That's how we can make a switch. This is a piezo motor. And of course, these are metal structures so that it cannot rub against each other, which means what you do is you actually keep a gap, about 8 to 10 micron gap here, you can see, and then you put some EBG structures there, electroband gap structures, so that the electromagnetic signal doesn't leak out from one to the other. You can get isolation of the 80 to 90 dB. If you are trying to build a radar at this frequency, you do not have any isolators available or circulators available at this frequency. So you'll have to use this kind of structures as an isolator. So it works really well. This is the actual metal structures that we have. Again, the waveguide here is of the order of 400 micron. So these are the challenges that you'll have to do. How do you align them? How do you test them? How do you put it together? Packaging is a big challenge as well. And then you have to have a load, known load that you are putting together. We actually developed a load. Let's come to the semiconductor part. So if you look around, you need a synthesizer that is working at W band, that is 90 gigahertz. If you want to buy something, first of all, it's not available. Even if something is available, a synthesizer at this frequency will need at least 10 watts of power. And it's kind of big. Total instrument power for me is less than 5 watts, so I cannot use off-the-shelf synthesizer. So we came up with a SoC-based synthesizer working at W band, and it works really well, 90 gigahertz. You can see here, it's the very good phase noise. This is where the chip goes, but you'll have to put in a block. And similarly, we also developed a spectrometer that has 3 gigahertz bandwidth, 4,096 channels. Now, what are the challenges of using silicon semiconductor in space? I know you are a big, investing big in space industry, and we should use semiconductor in space, because if you try to fly your iPhone in space, it won't last for less than a millisecond. It is not going to last. Why? Because the chips that develop, they're not radiation hardened. 65 nanometer or lower node, they're actually somewhat okay in terms of radiation. You have to talk about a couple of radiation. One is TID, total ionizing dose, because these chips are going to be in space, exposed to radiation for a long time. So what is the total ionizing dose it's going to see? And also on top of that, single event upset, because there'll be a big cosmic ray come in and upset your device. So you'll have to really think about those things. However, we have not really paid attention how to qualify them. When we are using a SoC, if you look at an old generation of chips, you have a voltage, a current changes. So if you put in certain conditions and measure those changes, you can say, okay, I can qualify this chip that is going to survive. SoCs are not like that. SoCs has built-in calibration system inside. If you put a voltage, measure a current, you won't know anything about that chip. You'll have to put in a board, you'll have to see the functionalities of these, put it in radiation environment and check what is going on. For that, you need to put in a board. You cannot put quartz part on the board. I'll give an example. This synthesizer board, if you put quartz part, and this chip doesn't cost much, about $1,000 perhaps, or $2,000. And if you put quartz board there, total cost of the board will be of the order of maybe $2,000. But if you put space qualified parts, this entire board will cost $300,000. And to test them, you'll have to test hundreds of them. So that is not possible. So how do we really tell our mission safety people that, okay, these are okay when we fly them? So this is the challenge that we face flying semiconductors in space. So we are trying to figure it out. We have been flying a Snapdragon from Qualcomm, but we got a waiver. We did not qualify them. We could not qualify them. So we are trying to figure out what to do. So these are the same challenges you are going to face. So we are trying to lay the groundwork for you. Hopefully they will agree that whatever idea that you come up with to qualify it will work. Okay, let's move on. So we actually put everything together. And you can see here, this is our WhatsApp instrument. This is a shoebox-sized satellite. This is with the lens. And we flew, again, this will give you the size. As I said, very small. This is the entire instrument. Idea is that it's all ready. We are going to go to a comet. Right now, we are waiting to get a ride. Idea will be that we make multiple copies of the same instrument. When a mission is going to Mars or somewhere, they will throw us out on the way. We'll have our own propulsion system. We'll go to the nearest comet, do the measurement, send the data back, and we'll have multiple data points to actually answer this question for once and all. Did comets brought water to Earth? Why this is important? Because when you are trying to find life on other planets, we'll have to find how the water went there. Is there water there already? So that's what we are doing. Actually, we put them on when you are building something for space, we'll have to also validate it. So we flew it on a high altitude balloon mission. So we put it on a gondola, our instrument, and flew it on a balloon mission. Here you can see, we put everything together. I have a video here that shows how the balloon launch happens. You can see here, this is a balloon. This we flew from Palestine, Texas. So when the balloon is launched, and we are holding, this is a handheld launch. Someone is holding our instrument here, you can see, very high tech. So you just go and release them by hand. And then it goes up to about 120,000 feet. And it does the measurement in space from 120,000. It's kind of analog we are trying to see, and does the measurement to see, did it work? And we validate all these missions. So right now we are ready for a launch, and then we got the data back from there. You can see here, this balloon has a small parachute after it lands, crash lands. Unfortunately, that parachute didn't work. So we crash landed at 40 miles per hour. And you can see here after it crash landed, and what happened is only thing that we broke was our lens antenna. But everything else worked very well. So which means that we won't have to do any shock testings for this kind of missions. It worked very well, and we got the data. We actually measured oxygen for this because at 120,000 feet, because of the pressure broadening, H2 line is too broad. You cannot really measure them. So again, so the idea that I'm trying to give you here, that whenever you are building something, you are trying to answer a big science question, you'll have to innovate, solve these problems, and validate whatever you are doing. It is not that put something together, test it in the lab once, write a paper, and you are done. That is not how space missions work. You'll have to go through all this thermal cycling, radiation testing, and everything. And we actually shown that it works. And you will hear from us very soon when we get a ride and do this measurement. Thank you very much.
Bismillah, salatu wassalam, rasulullah, assalamu alaikum. Good afternoon, everybody. Is it clear? Can you raise it? Okay. Good afternoon, everybody. My name is Hisham Shiger. So my talk is titled Space Semiconductors, and I'm going to talk briefly about advanced materials and emerging technologies, which we see as the two major players coming in the future. So we just saw a wide variety of applications, space missions. So I just thought I would summarize maybe the most prominent or the maybe well-known missions. We saw just briefly about the Voyager 1, Voyager 2. There was actually a mission by the Russian group Venera. So this was sent to Venus. So this was actually the first mission to return data from another planet. So as we see these different missions, we realize that semiconductors plays a huge part in the success of these missions. And this is an example where the electronics actually failed in the Venera mission, and there was some overheating as soon as they landed on Venus. So design constraints must be taken into consideration. And one thing I wanted to point out here is we see the difference in size between the Voyager 2 and the James Webb Space Telescope. So just to give some examples of design constraints that we have when we design semiconductors for space applications. So we can see here we have solar wind, we have other types of radiation, whether it's cosmic, trapped, or ultraviolet, and we have a list of design constraints that engineers have to adhere to, whether it's the complex integration process, the harsh environment of temperature changes, and mechanical stresses during vibration, in addition to making sure that it's mini, lightweight, and a reduced cost. And there are vacuum conditions in addition to mission-based criteria. So what are space electronics, or what are the main applications we've seen for space electronics? So as we know, satellite communication systems rely heavily on space electronics or semiconductors, remote sensing and observation technologies, positioning and navigation systems, in addition to scientific exploration. As we can see here on the bottom diagram, just to show the complexity and the number of devices that are needed to bring a space exploration mission to life. So these design constraints can be grouped into what we call fundamental requirements. So there's 4 main fundamental requirements that we must adhere to. So being extreme temperature resistance, so being resistant to extreme temperatures, the radiation shielding and tolerance, either through the device itself or through the packaging, the mechanical strength and durability of the electronics, being able to withstand the vibrations during launch, as well as maneuvering and in some cases landing. Finally, the thermal conductivity and dissipation. So this must be taken into consideration when these electronics operate in these harsh environments. Just to give a glimpse into the state of the art for materials, as we all know, silicon is one of the big players in semiconductors. 2 of the main applications we've seen are silicon carbide as well as silicon on insulator. And this has been due to their thermal conductivity as well as having a wide band gap, in addition to being radiation tolerant. So GaN is a big name, as we've seen in the previous years, gallium nitride. This is another material that has seen success in space applications due to its high electron mobility, as well as its high breakdown voltage and high operating frequency. In terms of the materials needed for packaging the electronics or needed for the circuits of the electronics, there's 2 main examples that we see here, either polymer-based or ceramic matrix composites. And this is an example of how the integration can be done with different layers of circuits and how to design the housing based on the electronics. moving into emerging materials and technologies, from what I found in the research, there's 4 main emerging materials for space electronics. The first one is 2D materials, and some examples include graphene, as well as transition metal dicalcogenides. Quantum materials, that's another hot topic we've heard about. 3D metamaterials, as well as organic electronics. And so I'm going to touch briefly about quantum materials, given that it's kind of a new exotic topic. So this was some research that we've seen from Dr. Tomohiro. And the interesting part of this diagram is to understand how these new techniques will be translated into new applications. So what we know as quantum or quantum devices. So one example is the quantum magnet, either as a functional material like we saw previously, superconductivity, as well as the topological state. So these breakthrough techniques are being used to realize quantum devices. Some other challenges and constraints for designers when it comes to space applications. And this is something that we heard over today's talks, one of which was the environmental impact and sustainability. But as we saw in the previous talk, the integration strategies must be taken into consideration during early design phases. Scalability and cost effectiveness, we're talking about sending things of high weight, and as we just heard, it takes 7 years to reach different parts of space exploration. So we have to get this done right, and we have to get it right from the beginning in terms of low cost and being able to scale up. Environmental impact and sustainability has to be taken into consideration when we design these electronics and what the future we expect in the sustainability of this. Regulatory and safety compliance measures are also essential to space electronics. Some of the work that we have at KACST, we have Professor Mohammed Amir with us today. He's been helping support putting this presentation together. So this is some of the work that he's realized in his lab. And one of the materials they've been looking into is this beta tellurene oxide. It has a large band gap of 3.7 electron volts, high electron mobility, and as well as a p-type conductivity. And so what they've realized in the lab that this actually is an oxide semiconductor that exhibits a wide tunable band gap between 1 electron volt to 8, which is suitable for space electronics. So 2 main applications we've identified for this technology has been for micro LEDs as well as optical systems. So in conclusion, what's next for space semiconductors and this industry? So what we've been looking into is what they call high-performance computing on board. So in order to complete these missions, we're going to have a lot of autonomy on board on the device. So this has created an opportunity for embedded systems, and one technology that we've worked at in the Center of Excellence for Aeronautics and Astronautics is vision-based navigation. So in order to realize vision-based navigation, we need this onboard computing capability. Finally, smart sensors and detectors. For these smart sensors, in order to be able to complete missions and gather data efficiently and autonomously. In addition, we talked about the quantum detectors, historically infrared and near infrared, as well as ultraviolet. Just to keep the talk short, thank you very much.
Good afternoon. So As you can see also, there is a question in my title, which is much less exciting than some of the questions before about the life in the universe. So what we are trying to consider is if we can actually use right now artificial intelligence on board of a satellite in order to do failure detection, isolation, and recovery. So we want to actually see if we can do this right now, or we need to actually rely on the next generation of the semiconductor technology, or say next generation of computing power on board. So what is represented there is a satellite with, on the right, there is some part of the detection of the satellite, which is a reaction wheel, which is nothing like an electric motor, which is used to move the satellite into the orbit, into different positions. And what can happen is that you measure all the sensors related to this reaction wheel, and you can have actually the current, the temperature, the speed of the reaction wheel, and also the voltage that controls the torque. And as you can see, you have at some point several spikes. Not necessarily these are an anomaly. What happens is that the last spikes is actually correspond to an anomaly because there is also a spike in particular with the speed. So if you have all this telemetry, in general, what you do, you transmit the telemetry to the base station, and then you actually perform anomaly detection after having done all this transmission. The idea is, can I do this on board, or I really need to transmit those signals? In order to try to detect these anomalies, what I need is to design a suitable detector, which entitled in considering, based on the signal that I need to measure, I compute a score which depends on the signal. And after considering the score, I need to, based on the statistic of the score, consider basically a threshold and determine if I have an anomaly or not. So I transform this score into a binary variable. And of course, before applying a signal to my detector, I need anyway to do some preprocessing. So there are basically two different families for making prediction and anomaly prediction on board. One is do prediction by compression, and the other one is doing, detection by compression, and the other is detection by prediction. So what I can imagine of doing is to have actually an encoder and a decoder which has been tuned to a specific family of signals. Or if you want to see if this is in particular a neural network, this has been trained by some data which correspond to signals which are correct. So you may expect that if you have then an anomalous signal, when I'm going to perform the encoding, so I compress the signal, and then the decoding, which is the inverse operation of this one, I reconstruct the signal. So if the signal is not anomalous, then the recovery is basically almost identical to the signal itself. If instead I have an anomalous signal, I have a very high anomaly, and I can easily detect if there is the anomaly or not. Or I can do prediction. So what I'm doing here, I take a predictor, and then I'm taking a previous version of the signal. With this previous version, I'm making the prediction into the future, compare the future version of the predicted signal with the current version. If there is a huge mistake, then again, I have an anomaly. So typical example of machine learning algorithm which are of the first kind are a simple principal component analysis, or a more sophisticated autoencoder, which is a kind of neural network. Or for the second one, I can use a simple machine learning algorithm like an autoregressive moving average, or I can use something more complicated, which is a recurrent neural network, which is called log short-term memory. This is one of the examples, so in order to keep the presentation short, I give you some details only for the architecture of the autoencoder. The autoencoder is actually nothing but a first neural network, which is moving the input signal into a latent space, which is a reduced dimension vector, which is actually represent all the information that I want. And then with the inverse of this encoder, I'm going to re-expand this vector here into theoretically the same version of the signal that I have here. So if the two are very different, then I can see that whatever I had at the beginning is an anomaly. This is a typical structure of an autoencoder. As you can see, there are several layers of a neural network. So the first one is there are convolutional one-dimensional autoencoder, and then the last one is a dense layer, and then the inverse for the decoded one. Of course, the trick is that I have to have the signals which are non-anomalous in order to train the network before I can take any decision. And these are the example of the training. These are data of a real satellite which are given to us by Thales Alenia. So you can see this is 1 year worth of data. And what I'm measuring here is actually the mean square error, which is actually my score. So there are, in general, the value of the score is very low, there are some spike. And if you take the statistic of the distribution, you can see that most of the value that I consider are basically very low, and some of them are very high. So I can get a potential threshold in order to determine that all these cases are actually anomalous. And if I'm doing that, and I present my network with a test set, so this is actually, you see, in this case, there was an anomaly because at some point after that, the mean square error completely get a different kind of behavior. But recognizing this spike with respect to the other one is extremely difficult. But using this threshold value, what you get, in fact, is that you are able to recognize the anomaly. Well, the problem is doing this is easy if I have all the signal. What about if I want to put them on board? So using some of the computing platform that exists already on board of the satellite, like a GR740, which is exactly the platform on board of the satellite we consider, or something similar, which is an ARM Core M7. This is not a RAD version, but it exists an equivalent architecture, which is RAD-R, so the performance are actually the same. So how can I make sure that all my algorithms can actually be run into this platform, especially if they are very complex neural network? Well, I need to do some tricks, which are basically model compression. I can actually add quantization, or I can prune the network, which means that I simply remove some of the interconnection in my neural network, and there are several ways to do that. And I can even do some iterative pruning. So I prune the network, I retrain it a little bit, I prune the network, I retrain it a little bit, and so on and so forth. And with quantization, same idea. I can use fake quantization, which is a trick in order to take into account that I'm going to quantize the neural network in terms of the weight when I'm training it. So I'm applying all these techniques, and these are the results that we were able to get. All these data here are actually real data taken by some mission from the European Space Agency, but I had not the permission to reveal which kind of data there are. In any case, you can see that the value of the average error is the lowest for the most simple algorithm that we get, which is the autoregressive one. And also the one-dimensional autoencoder is performing reasonably fine. And this is when I don't apply any quantization of pruning. If instead I consider the time for taking my decision, you see that the autoregressive is the fastest one, so it works more or less in real time for this kind of system. PCA and the convolutional autoencoder give more or less a similar performance, while the long short-term manager is actually the slowest because it's the most complicated network. If you apply quantization and pruning, what you get is that, again, the best performances you have with the convolutional autoencoder, which becomes similar to the autoregressive model. so we can actually apply it on board of the satellite, while the other one are doing more error and are certainly slower. So to conclude, the good news is that yes, semiconductors are enabling AI even on board of satellite and even for the architecture that we have right now. The bad news is that, of course, the performance depends in particular on the anomaly that need to be detected, and the one that we have were relatively simple, so one need further studies in order to detect what I can use on board of the next generation of satellites. For instance, if I want to perform some image processing, assume that you want to transmit the value of your imaging, your satellite imaging to the base station, but then the imaging has been blurred because is a bad picture, or because you are actually simply taking pictures of clouds because there is coverage of clouds, you don't see anything there. Then you cannot use the architecture that you have on board right now. They are not powerful enough, as was mentioned by the previous speaker. You need more performing architecture, like the one based on RISC-V. And the other angle that one needs to consider is to do dedicated architecture also on board for potential doing even on-board training for space mission. And it's certainly true that the model that you use for AI is fundamental. So my final message here is that, yes, it's important to have new semiconductor technology. Yes, it's important to have new architecture, but it's also important to co-design the algorithm that you want to run on board. And with this, I thank you very much for your attention, and I hope to see you around. Thank you.
Assalamu alaikum. Good afternoon, everyone. Presentation. Okay, so keeping on the topic of semiconductors in space. So these are the class of assets that we actually put up in space. So starting from the International Space Station on the extreme, on the top right-hand corner. And then on the bottom, you've seen the James Webb Telescope, essentially. And by the way, that took 10 years in the making. In the middle top, you see a whole class of launch vehicles. And I should also mention that tomorrow is kind of a pivot point for space exploration. SpaceX is launching the Starship, the 4th test. And if they're successful, that will revolutionize space exploration going forward. On the bottom, we have ground segments. They talk to a whole suite of satellites, and we call that telemetry, tracking, and command. And on the top right is a whole class of satellites that's orbiting Earth. Currently, there's about 9,000 different satellites that's orbiting the Earth that are operational. And at the bottom, I should mention radio telescope. I had the privilege of overseeing this project. It's the most sensitive radio telescope being built at the moment. The one that's in the bottom is called the Meerkat. It's 64 dishes. And when it was switched on, we discovered 1,300 new galaxies never seen before. But this forms part of what is called the square kilometer array, which will pencil back right into the beginning. I think Dr. Khoutem mentioned the Big Bang, or what we call the epoch of reionization. Especially on the right-hand end, you need a lot of processing capabilities. For example, the radio telescope, the data volume is about 10 times the internet traffic. And we're looking at planar phase arrays, which takes it about 100 times the global internet traffic. So some of these technologies are pre-competitive and they don't exist. So we have to do a lot of work in terms of developing new technologies. And in all of these assets, semiconductors is essentially the backbone that powers them. Given the SpaceX theme, I'll just give you a class of control units, for examples. On the left-hand side is your guidance, navigation, and control system. And you can see that fits on the top end of the launch vehicle, which essentially provides control guidance of the launch vehicle as it gets into space. And that includes inertial measurement units that calculate the acceleration and the orientation of the launch vehicle. And you also have a star camera, which essentially tracks the footprint of the stars to give you a sense of the orientation of the launch vehicle as it goes into space. And all of this is powered by semiconductors as well. And just to look at the transition from the Apollo mission to what is now called the Artemis mission. In the Apollo mission, they used these first semblance of what I call the semiconductors. So that's essentially 8 resistors with 6 transistors plugged together. And that was used in the Apollo mission for landing on the moon, essentially. And on the top end is 4 of your innovators that actually put the system together. In the Artemis mission, especially on the Orion capsule, we'll be using the IBM PowerPC 750, essentially. So there's a huge transition from where we started to where we currently are at the moment in terms of semiconductor technologies. So I think some of this aspects has been covered before. When we're looking at performance in space, it's a very hazardous environment. So we're looking at triple modular redundancy, meaning that we cannot afford critical point failures. So we have to build in dual, triple, and sometimes quadruple redundancies. So if there's a failure in one area, there's a backup to cover that failure. It's also a very harsh environment and radiation hardening. I think we provided the space environment, the space weather aspects. And by the way, there's an area between Southern Africa and South America, which is called the South Atlantic anomaly, where the Earth's magnetic field is very weak, and there's excessive radiation that comes down. And when satellites move across during very active solar activity, a lot of the satellites are damaged because you have what is called, it kind of gets into the electronics of the satellites and it saturates it. So you damage a lot of the satellites going through there. Power efficiency and miniaturization. In the Apollo, when they first started on the computing capability, the computers were the size of fridges, and that was not acceptable in terms of the mass, because the mass is, to get a kilogram of mass into space is very expensive. So they had to bring it down to a shoebox size, essentially for the Apollo missions. And then longevity and reliability is also very critical. So if you're looking at low Earth orbiting satellites, they should last between 5 to 7 years. Geostationary satellites last about 15 to 20 years. So you need semiconductors that can last in that harsh environment and for that long periods of time as well. And then ruggedized for vibration and thermal and shock events. So if you think of a launch vehicle as it takes off, there's a lot of vibration. So your electronics needs to survive that transition into space as well. And then just to give you a sense, the market share in terms of semiconductors used in the space industry, we're currently in 2024 sitting around $3.8 billion of semiconductor value used in the space sector. It's projected that by 2032, we should be using close to $6 billion of semiconductors in terms of space exploration. But if you look at it in terms of a regional perspective, the biggest users of semiconductors in the space sector is North America, followed by Asia Pacific and Europe. And you'll see that the Middle East and Africa is using just around 1%. So that's currently a very small slice of the semiconductor market used in the space sector. But I think given the growth, like with the Saudi Space Agency and the National Space Program that we're looking at, and even in the Middle East region, and even Africa, in the last year, the 5 years, we've seen over 20 new space agencies. So there's a whole new growth coming into the space sector from the Middle East and African region as well. So that will obviously expand as we go along. So we've seen the demand of semiconductors used in space exploration, but there's a flip side to this, the use of microgravity. And last year we had 2 of our astronauts go in the X2 missions, Astro Rayana and Astro Ali. And it's interesting, some of the experiences they convey to us in terms of what they experience in space. And in fact, we asked Astro Rayana last week, what is the most funny experience you had in space? And she said, when you drink water, it doesn't go down. You have to gulp it to force it down. So just some effects in microgravity. There's the absence of buoyancy and sedimentation. So your heavier materials would sink and your lighter materials would float. In space, that doesn't happen. You have an equal mixing. Okay? There's no gravity. The same with in terms of convection. If you watch a pot of water boiling on a stovetop, you see these convective currents. That doesn't happen in space. It's uniformly heated, essentially. And then also hydrostatic pressure. If you've ever flown on a flight and you've taken a bottle of water with you and then you've drunk it and you kept it, when you land down, the bottle is crumpled. That's because of hydrostatic pressure. In space, you don't have that because there is no such pressure acting on it. And then there's the absence of containment requirements as well. So there's some advantages of actually using microgravity as a production lab as well. And what you see here is some of the first crystal growth and purely geared towards semiconductor production. But this is in the Sky Lab in 1973. You see some interest in terms of crystal growth, germanium, indium antimonide, and germanium monoselenide. So you've seen crystal growth's interest in space in 1973, and this shows the experiments around crystal growth and the microgravity area. So the primary experimenters are US, Russia, and China. And you see there's a phenomenal interest around about 1995, but that's when the previous space stations like Skylab and Cosmos were decommissioned. And in 1998, the International Space Station came into play. So you see, again, some renewed interest, but not as much as the earlier years. But something interesting is happening. NASA has commissioned private companies to start looking at commercial space station. So the first contract is with the Axiom, who will take up a module, dock with the space station, and keep on adding modules. And the idea is that by 2030, the International Space Station will be decommissioned, and Axiom will essentially own a private space station. But there are other companies like Voyager, Sierra, and VAST that are also looking at putting space stations in orbit, which means that there are more experimental platforms for microgravity that's coming through. And that obviously sees, and they're looking at it more from a private commercial point of view, for example, pharmaceuticals, new alloys in space as well. So we're going to see some new interest in crystal growth in microgravity. And so, as you see here, there's interest in many missions to the moon and to Mars, and we need a whole host of assets that we need to put down. And we're starting to look at what we call in-space manufacturing. So actually manufacturing some of these space assets in space as well. And obviously we will look at even semiconductor production in orbit as well. So that's essentially where we see the new era going around in terms of new experimentation, new platforms, new materials being produced for new exploration missions. And just as my last slide, the advantages of manufacturing in space. It's naturally a clean environment. It's a very sterile environment. You also see now 3D printing being done on the International Space Station. So we're looking at microelectronic printers being put up into the International Space Station. And then the benefits of microgravity, as I showed you in earlier slides, improved material properties and uniform layer depositions as well. So that's more on the production side. So thank you for your attention.
Hello. I would like to thank all the distinguished speakers. Please join me in the panel discussion. Hello. Okay, thank you all for attending this session today. I also would like to thank all the distinguished speakers for their informative talks. Let me start with Dr. Val. How the space semiconductor research fits with the 4 national priorities in the kingdom?
So one of the national priorities is the economies of the future, and the space sector is actually embedded, is one of the areas. The space sector is actually one of the areas under economies of the future. And I think if you look at the RDIA strategy, there's a big focus on placing Mars a habitat by 2040. And so from the Saudi Space Agency perspective, we're working on what we call the RDI roadmap, a research development innovation roadmap. And that's essentially encapsulating all of the technologies we would need between now and 2040. And that includes components or platforms for satellites in low Earth orbit, microgravity experiments. And over the X2 mission, we had about 14 different experiments. We want to see a lot more of that happening. And then also space exploration missions as well. So this is how the National Space Program fits into the RDI strategy, which is under the economies of the future. Thank you.
Dr. Hisham, what are the advantages of manufacturing semiconductors in space compared to the manufacturing in the ground, in the Earth?
So, yeah, that's a great question. I think that it was nice to see the earlier talk, they talked briefly about this. So I think this point of having the microgravity, so being able to manufacture in a microgravity environment, this is one of the first differences or benefits that we've seen with the crystallization in space. So the obvious one is the reducing of costs. I think the first speaker made a good point that let's assume, we make it to one of these planets. We're not going to have the ability to drill holes and do things that mechanical devices that are needed. So I think being able to send, this idea of 3D printers, being able to manufacture on planets in space. We've seen a lot of success in the International Space Station with this. But I believe the main benefit would be the reducing costs and then ensuring the robustness of the mission.
Thank you. Professor Gianluca, how do you see the market for space semiconductors evolving in the next decades?
I mean, space is certainly the next frontier, and the possibility of utilizing semiconductor in the implementation of the either just satellites or even for commercial application. It's certainly something that will be growing tremendously because you will add new functionality, and also there will be additional possibility for usage of either device in space or mission that you are doing. So I would say that it's going to be growing in every possible dimension. And I mean, it has been also indicated in terms of the plot that was already put in the chart. It's can be even a pessimistic interpretation of that.
Thank you again for the distinguished speakers.
Okay, hi. Thank you, organizers of this forum, for inviting me to give a talk here. And I'm going to actually talk a little about what is not particularly considered to be normal conversation. People normally think that silicon is the solution for millimeter wave applications, but I think that GaN will be better going forward, and I'll try to convince you of that. So the gallium nitride is a very, starting from what Shuji did with the LEDs, there are many applications for gallium nitride, which is basically, where is the, do I have a pointer? Not really, okay, fine. There are many applications for gallium nitride in the electronic space, which is airborne radar, data center power supplies, of course, solid-state lighting displays, and then we'll be talking about base stations here, but there is a huge market also for power electronics, and that's in the energy space and also in the electric vehicle space. So the mega trends that are existing today in electronics is basically about in the charger space, smartphones and chargers for smartphones, laptops, and then also, of course, power supplies for crypto mining, AI, and so on and so forth, electric vehicles, and then, of course, there's the 5G, 6G RF infrastructure space. And this talk will focus only about the RF space. So high performance, low cost gallium nitride is the preferred next generation semiconductor for multiple RF applications, high performance and low cost. So semiconductor technology has to be high performance based on application. There's a big difference between MIMO and phased array. In phased array, you got to steer the beam, and in many MIMO applications, you do not. When you do not, gallium nitride plays a very big role. And then it has to be very reliable. It has to have a roadmap for lower cost with every generation. And low cost requires wide market penetration and vice versa. You cannot have a low cost technology which is niche. That violates the second law. So you should basically, if you want something cheap, it has to be very widespread. And gallium nitride satisfies all these requirements with a higher performance to cost ratio. So now this is an important slide, and it depends on where you live. For example, if you want to transmit millimeter wave signals or any RF signal, you find out that in general, the attenuation is the loss of the signal per kilometer, goes up with frequency, okay? And the higher the frequency, the more resistive the transmission through air, effectively. But there are minima in this resistance, and these minimas are open windows in transmission where the molecules in the air do not absorb the microwave radiation. And these are the frequencies of interest for us to develop technologies. Also note that rain is a huge impediment to millimeter wave transport. So if you're going to use millimeter waves in India during the rainy season or in Riyadh where the rain is less, you have a whole different transmission in air. Riyadh will be much more forgiving to microwaves. In India, it'll be much harder. So it depends on the deployment conditions and also the scale. And I'll talk about this more later. What we'll be talking about are transistors, and basically you need high efficiency, high output power, and low system cost. One of the most important costs in millimeter wave transmitters is cooling the system. And so if you don't have efficiency, this is going to be a very expensive proposition. So this is 5G low band. This is called 5G mid-band. It goes to 6 gigahertz. This is where a lot of the deployment is happening today. This deployment in the 600 megahertz to 1 gigahertz 5G, this is mainly in China because the band was available. But in the US and much of the world, this is where 5G is, around 2.6 gigahertz up to 6 gigahertz. Now, when people talk about 5G, there's also a high band of 5G that is 24 gigahertz and up. Now, what people are looking at is what is called the mid-band. Mid-band is between 7 and 24 gigahertz. This is a very exciting frequency range because here the transmission of microwaves is quite readily happening, whereas in 28 gigahertz, you get a large attenuation of the signal. So I'll skip this. Oh no, actually, wait a minute. Millimeter wave applications are myriad: satellite communications, automotive sensing, radar communications, medical therapy and body scanning, virtual reality and HD video, basically transmitting the information directly to your AR, VR set. I'll be only talking about 5G communications. I just want you to remember there are some terms and they all refer to efficiency. You need power because without power you cannot transmit. You need efficiency so that you don't generate too much heat. So you need both output power and efficiency. Now there are many device milestones, and thanks to working with Steve, Shuji, Jim Speck, and others, a lot of these milestones happened in Santa Barbara. Of course, the ALGAN-GAN HEMT was first demonstrated by Asif Khan in 1993, but microwave power HEMT was first demonstrated by us at UC Santa Barbara, and then we showed we could make power electronics, we could do polarization doping, we could do nitrogen polar GaN, which is a new form of GaN. So all these developments happened at UC Santa Barbara. So it has been kind of the birthplace of a lot of gallium nitride electronics. I'd like to emphasize one thing. The gallium nitride HEMT is the first electronic device platform based on polarization. Before this, there was none, and there is none other than this up till today. So we made the first GaN RF transistor in 1996. And this was, when we first made this, we got 1 watt per millimeter. Now that was a lot because it was equal to what was actually available at that time using gallium arsenide. So we said, oh, this is great. It matches the current best technology. But to make a technology really be employable or accepted, you have to have 10 times the improvement. If you want a new technology to be widely accepted, if it is 50% better than the current technology, don't even bother, because the current technology will improve with time. So it is very important to have 10 times better so that by the time you actually get into the market, you're 3 times better. That's key. And then development must be rapid, because if it takes too long, the incumbent technology will overtake you. And what we had to do for these two to occur, we had to solve what was called dispersion. Dispersion is when you have a transistor, it looks like this at DC, but when you try to switch it, the current collapses. And this is all due to surface straits. I think it was the great physicist Dirac who said that the surface is the devil's workshop. So that is absolutely true. If you have a free surface anywhere, you have a problem. So this free surface was then a source of a lot of the problems, but we got rid of it by using appropriate passivation and also using this technology of a field plate to relieve the electric field. This gave us increased breakdown voltage and less dispersion. Then polarization engineering again. We used a thin aluminum nitride layer. This aluminum nitride layer is only 6 angstroms thick, 0.6 nanometer. And with 0.6 nanometers of aluminum nitride, the mobility of the gallium nitride layer went from about 1500 to 2200. This is the magic of polarization engineering. 6 angstroms improve the mobility by 30%. This was also an invention at UC Santa Barbara. And then by doing a lot of these things, we went from 1 watt per millimeter to 40 watts per millimeter. Now you see you have that 10x improvement. People told us that millimeter waves gallium nitride would never work. In fact, there was an argument you should not even fund it. Luckily, some of my friends in the Navy did not listen, they funded it. And then all of a sudden, we got terrific performance at 40 gigahertz. All right, that's great, but the efficiency was low. Now, if you look at gallium nitride, compared to every other material system, don't worry about this chart, you'll see that the output power from gallium nitride is better than every other material all the way to 100 gigahertz. No other material matches it. Gallium nitride is also polarized, is a polar material, so you can do very clever things, like we can do polarization grading. This was developed at UC Santa Barbara, where you change the aluminum composition, no doping involved. You just change the aluminum composition and you get the doping based on the slope of the grade, the rate at which you change. And then this was done by, now they're all professors. Devjeet Jena was a student then, now a professor at Cornell, and Siddharth Rajan was a student then, now a professor at Ohio State. HRL is using the same thing. We call it a pole FET. They call it a graded channel HEMT. And they've used it to get very high linearity. There are other technologies being developed called a bridge HEMT, where people are stitching a gate and gating the two-dimensional electron gas from either side, much like a FinFET. This is also another version of it called the Slick FET from Northrop Grumman. This is from Teledyne. Aluminum scandium nitride, we are working with KACST on aluminum scandium nitride, a very important material system which has very high polarization, as you can see here, and also can be potentially ferroelectric. And so this is another new material that we find very exciting to improve performance more. But what I'm most excited about at the moment, until the aluminum scandium nitride becomes successful, which we are sure it will, is nitrogen polar. Nitrogen polar GaN is taking gallium nitride and just flipping it. If you take silicon and you flip it, nothing happens, it's still silicon. But if you take gallium nitride and you flip it and it becomes nitrogen polar, you get a completely different material. It's magical because that's what polarization does. It maintains the sense of the orientation of the crystal. So now we did that, and then what happens is everything changes. In gallium polar GaN, aluminum gallium nitride sits on top of gallium nitride, and the two-dimensional electron gas is below the AlGaN. Nitrogen polar GaN sits on top of the AlGaN, and the two-dimensional electron gas is on top of the AlGaN. So it's an inverted structure. Now we've made a very complicated device to look at, but over time, everything is complicated until you do it. After you do it, it becomes simpler. So this is a device we built. This is all grown by MOCVD and in Steve's lab. You basically have, we do it on both silicon carbide and sapphire. Please focus, not focus, but note sapphire. This material is grown on both silicon carbide and sapphire, and it's flipped. So the two-dimensional electron gas, the gallium nitride, is sitting on AlGaN. And then we have an AlGaN cap on top. This increased the breakdown voltage of the gate on top, we have an insulator underneath, and we also have an an undoped gallium nitride cap. Because of the polarization of the material, and we don't have time to get into it, but the most important thing is, as you grow the GaN cap on top, the amount of charge in the two-dimensional electron gas increases. By growing GaN on top, the two-dimensional electron gas conductivity increases. So we have a way of just controlling the amount of charge here by just growing more material on top. And this is a very cool thing, and what it does is it gives you a complete breakthrough performance. This is gallium polar GaN, traditional GaN, and this is a W band, as the previous speakers had talked about, it's at 90 gigahertz. And you see that the filled dots is on silicon carbide, and the empty dots is on sapphire. Gallium nitride on sapphire, nitrogen polar GaN, has a performance which is as good or better than silicon carbide, and sapphire is $60 for a 6-inch wafer, $100 for a 6-inch wafer, compared to silicon carbide, which is 10 times that. So we're very excited about this. And so it consistently performs, nitrogen polar GaN consistently outperforms gallium polar GaN in the metrics of output power density and efficiency, even on sapphire substrates. So that's watts per millimeter, but how many watts do you get from one device? At 94 gigahertz, one device gives you 712 milliwatts. This is quite spectacular. For people who are in the W-band business, one device typically gives you 10 milliwatts. But now what we've got is we've actually demonstrated 1 watt. So here's a benchmark, nitrogen polar GaN, and this is the rest of the world, and this is the rest of the world includes the industrial world, and this is what we've achieved at UC Santa Barbara, completely out of the picture compared to the gallium polar GaN. We've also made Schottky HEMTs, which were not considered not possible, but we've just developed a titanium nitride Schottky barrier device from this device for this material. And you get, it's a very nice device in the sense that it gives you very high performance, 300 gigahertz Fmax from a nitrogen polar HEMT. Remember, people thought you couldn't even do 30 gigahertz. This is 300 gigahertz. And most importantly, the efficiency is stunning. We are getting 53% power added efficiency at 94 gigahertz. Nothing comes close to this in any material system. Remember, to make a system that's cheap, you need high power, high efficiency, and a low-cost device. Nitrogen polar GaN, in our particular instance, I believe, does exactly that. And so this is a benchmarking. This is conventional gallium nitride and what we are all buying from suppliers today. That's the red dots. And what you see in the green star and the red and all the open blue and filled blue circles is nitrogen polar GaN. So I'd like to just conclude by saying that, in my opinion, high performance, low cost gallium nitride is the disruptive technology for millimeter waves going forward. Millimeter wave deployment has become saturated. Why? It's saturated because of cost. If you don't have, think about it. When Shuji first made his blue LED, to buy one blue LED was $1. Once it became commonly used, that same blue LED today is 1 cent at that brightness. So if you don't make things cheap, it's just it's Gucci versus or let's say, yeah, you don't want to be a Gucci technology because semiconductors are not that. And so I'd like to just conclude by saying that many people think gallium nitride is expensive. I'm here to tell you they're wrong. Thank you very much.
Thank you. Thank you very much. I would like to thank the organizer for inviting me and for giving me this opportunity to give this presentation on beyond 5G or 6G and our perspective on what this vision should be. So as you know, as we are aggressively deploying 5G worldwide, from a research perspective, we are active trying to develop beyond 5G and 6G networks. Obviously, main focus of the activities is on trying to, of course, outperform current system from a speed perspective, from a latency perspective, and from a connectivity density perspective. So these are the direction that were there already as part of 5G, and 6G is supposed to do better in these three important directions. But on the top of that, there is, of course, a strong feel that 6G should address some of the shortcomings of 5G and the earlier generation. One of these concerns that was further highlighted or emphasized during the COVID time is so-called connectivity or digital divide. Since we still have about 3 billion people, and this is according to the latest ITU statistics, that are unconnected or underconnected. And actually, the problem is beyond that, because we are living in a world where we don't need anymore to just connect people, but we need to connect also a variety of sensors, actuators, IoT device in hard-to-reach areas. So what I would like to mention is that essentially beyond 5G and 6G should be also about connecting the unconnected. And by the way, and I'm not sure why here the photo are not showing up, but it should have been some photo corresponding to these themes. When you do research, what I was trying to highlight in this slide is that trying or doing research in connecting the unconnected or connecting rural, hard-to-reach area can help in many other dimensions. In particular, it can help in post-disaster or emergency communication, in exploration mode when you send scientists in the middle of nowhere and you want them to video stream data, for military applications, IoT, as I mentioned, everywhere where you are not limiting yourself to smart cities and things like that, and for aerial mobility, aeronautic kind of connectivity, as well as maritime connectivity when you have ships in the middle of the seas. So as an example of some research that we have conducted from, again, mostly a modeling perspective so far, if you assume that a disaster hit a particular area, and in this particular area, you assume that essentially everything within that red kind of circle from a base station perspective is destroyed, you bring connectivity potentially from the air by sending drones. And what we were able to show in our analysis is that there is an optimum number of drones that you need to send given the radius of a particular disaster, because if you send too few, obviously you don't have enough drones to cover that area. If you send too many, they start interfering with each other. And actually, the second conclusion we reach, and that's kind of highlighted in the right figure, is when the disaster radius becomes too big, in the order of tens of kilometers, it doesn't make sense anymore to send drones. What you need to send is rather a high altitude platform. Basically, these drones or a glider that operate in the stratosphere and that have a much wider coverage area. And I will talk more about that as my presentation progresses. So one thing I would like to highlight is that why do we have this challenge? Why do we have the essentially connectivity divide? There are too many reasons. One important reason is that essentially when you look at this graph where we show quality of experience as function of the cost per user in remote low population density areas, then obviously, although optical fiber cable is the best from a performance perspective, it does not make much business sense to dig and lay hundreds, if not thousands of kilometers to reach these kind of remote and essentially often low-income areas. So in other words, there is no much return on investment. So actually what we want to achieve is the upper left corner, where we would like to achieve a very good performance, even when the cost per user in remote low population density area has to be low. And that's the challenge that we would like to solve. Now, one way to solve that, and that's one area where we are quite active, is to use what we can call tower in the sky. The technical word for that is high altitude platform station or high altitude pseudo-satellite. Last year, actually, so I mean, these kind of platforms, so they are operating in the stratosphere at 20-kilometer altitude. So just for calibration purpose, airplane fly at 10 to 12 kilometers, the airplane we take to move around. These will be operating at a higher altitude in the stratosphere, roughly 20-kilometer altitude. They come in different shapes. They can be balloons, airship or blimps, or fixed wing, and even sometimes aircraft. So the beauty of HAPS is it can bridge the gap between urban environment, where we can use basically standard towers to cover urban area with the small cells, and satellites, which tend to, of course, be very helpful in deep rural or deep maritime environment, and and you all know about the popularity of constellations such as Starlink and OneWeb. But anything in between, HAPS can be there for suburban areas, for offloading, or you have kind of a surge of capacity in urban environment, and even sometime in rural environment when it's not that very far from an urban deployment. So that's where HAPS sits. And last year we did an experiment in collaboration with CST. So CST is a Communication and Space Telecom Commission, Saudi Arabia. That's pretty much the equivalent of FCC in the US. This was an experiment with SPL, a stratospheric platform, where we demonstrated that actually with a standard phone, you can talk directly to one of these HAPS. So the beauty of a HAPS communication in contrast to satellite is that you don't need a relay in between. You don't need a box or an antenna to act as a hotspot. You can just use your standard phone to connect direct to the HAPS, and that can help essentially with the economy of scales to hopefully make connectivity more accessible and more affordable if we have this stratospheric platform up and running in the coming years. So one way to demonstrate the usefulness of this technology, as part of our experiment, what we looked at here is a comparison between a connectivity from a terrestrial base station in blue, and the figures on your right, and a connectivity from a HAPS in magenta. And as you see, as you move away from the center of the base station, you see that the throughput is going down. The blue kind of, let's say, rectangle are going down, and at some point you lose completely connectivity, whereas magenta kind of rectangles are staying quite high and stable, which means you maintain connectivity, although you are quite far from the center of the base station. And that's kind of what we are trying to prove, is that we can increase your area coverage by going high in altitude and deploy the stratospheric platform. Now, here we are, of course, in a semiconductor forum. What makes basically this challenging? So there is, of course, the aerospace aspect, which is beyond the scope of this forum. But from a pure electronic perspective, the beauty, again, of a HAPS, that you can use the same base station we use on the ground in the HAPS, with the only difference that it has to operate, obviously, in different temperature. So we are talking roughly at electronics that have to be up and running at minus 65 degrees Celsius. But beyond that, humidity is low, but I don't think it's a concern. So yeah, humidity, pressure is quite low, but I think it's not a concern from again, electronic perspective. So the only thing we need to kind of make sure that is, let's say, taken care of when you take some ground electronics and base station developed or designed for a ground base station in a HAPS, is that it's able to operate at relatively much lower temperature, roughly minus 65 degrees. So I would like to conclude, just to remain within the time allocated to me, that actually what makes this technology even more interesting, if you combine it with two other interesting technology, one of them is quite mature, one is still emerging, although it has been used as part of 4G and 5G. So the paradigm I would like to conclude with is this following paradigm, where basically you have an aerial base station. In this case, it's a satellite, but it can be a HAPS. And you have two sides. On the right side, we have what we call the user link. This is a massive MIMO beamforming capability that allow you with basically hopping of beams to go where traffic is. So this is, you can have hundreds of beams. Each beam can have, let's say, 10 gigabit per second, and this beam is moving to wherever traffic is needed. So that's one side of these aerial base stations. And then, of course, the whole traffic has to be, let's say, backhauled to the ground in order to connect to the internet. This is what we call in our jargon feeder links. Currently, this is happening Ka band, a band that is quite under competition because some of it IMT or cellular network want that band. Some of it actually we would like to use for user links because we are running out of Ku band, which is currently used for user links. So the other emerging technology that is kind of being pushed to help in this paradigm is free space optic, a technology that has been tested and validated in a ground environment, although it has some limitation due to atmospheric turbulence and basically kind of sensitivity to weather conditions. But when used for space, if we use some proper, let's say, atmospheric turbulence mitigation techniques, we can get this terabit per second feeder links that is in the analysis part of the spectrum because we are operating the optical part of the spectrum. So together, free space optics, a HAPS or satellite, or in other words, aerial base station, and massive MIMO with basically beam hopping is, in a way, the recipe to help to connect the unconnected. So with that, I would like to thank you, and I thank again the organizer for giving me this opportunity to share with you some of our work in this area. Thank you.
Okay, first of all, I'd like to thank as well the organizers for the invitation. I'm not a semiconductor guy, but I'm going to share with you my vision for 6G beyond 5G. We don't know what 6G is at this point. It's not standardized yet, but at this point, there are lots of research groups studying 6G, and they have their own vision. Salim already presented his vision of 6G, HAPS, MIMO, beamforming, and free space optics. I'll share with you also my vision. But before we go to 6G, 5G is still being deployed. At the same time, there is a lot of research going into the 5G. At this point, the community is studying beyond 5G, 5G advanced, So it's called Release 19. The first release of 5G was Release 15. And then after that, we keep updating 5G. So the latest update that we are working at this point is the Release 19. And for the next 18 months, we're going to be studying this. So what are the new things that 5G Advanced or 5.5G is going to bring to us? MIMO, of course, as Salim mentioned, is going to continue, has always been there. As the number of antennas are increasing, we have better beamforming capabilities, and there are many scenarios where we can utilize MIMOs. But the challenge in MIMO is implementation. The theoretical aspects and the different use cases are already been done, but when it comes to implementation, we are still struggling. One of the difficulties is channel estimation, and it requires a lot of feedback, a lot of pilots. So it's still an undergoing issue. Another problem that we are facing today is mobility. When everything is fixed, we can do magical things, but when the users are mobile, when the base stations are mobile, as in the case of satellites or high-altitude platforms, then the life changes, and many of the things that we are doing doesn't work anymore. As the mobility increases, the faster it is, the more problem that it brings. So currently we are still looking at to improve the communication under high mobile scenarios. We are looking at new topologies. Another thing that's discussed in Release 19 is self-organizing networks. As you know, I'm from Turkey. We had an earthquake last year. When the earthquake happened, we lost the network because most of the network components are on the top of the buildings. The building collapsed, the network collapsed. If there is no energy, there is no network. When you lose a couple of these base stations here and there, the network cannot self-organize itself. So this is one of the biggest issues that we are facing right now. The networks are not flexible, they are not adaptable, and we lose the communication. So this is a topic that has been studied over the last 20, 30 years, but when it comes to implementation, still a major issue. So in Release 19, we are studying that. Another very interesting topic from also semiconductor perspective is ambient IoT. Ambient IoT is basically a device that utilizes the energy, electromagnetic radiation out there, rather than requiring an anchor point. So it uses the radio waves and transmits information on the top of these radio waves. So a TV signal or a 3GPP signal, LTE signal, can be utilized to encode your information on the top of it and then transmit to another device. And the energy is also recovered from the ambient signal. So it doesn't require an external battery or any source of energy. So it's a very interesting way of increasing the IoT devices and increasing the lifespan of these devices. Salim already mentioned about satellite and non-terrestrial platforms, including HAPS. Another thing that's very interesting, again from semiconductor perspective, is low-power wake-up devices. So currently our radios are always awake and always consumes energy. The mobile phones we are talking about always checks whether there is something for him or not. And this consumes a lot of energy, a lot of processing. So we are trying to integrate another device into our devices, starting from IoT, low-power sensors, but later even to our phones, which we call it wake-up radios. So a radio next to another radio. This radio is going to be much simpler, possibly analog, and will run with minimum power as possible. But the only job of this radio is wake up the main radio. So our radios, the current radios that we are using are the main radios, but we need to associate that with another radio, wake up radio. And currently in release 19, we are looking at how to design these wake up radios and whether it should be analog or digital. Possibly it's going to be analog because of the power consumption and also because of the cost. We are looking at different options of implementing wake-up radios. Another very critical issue today is the network energy. Currently, our networks are consuming a lot of energy. When I talk about network, is basically base stations and the core networks, but most of the energy is spent by the base stations. I was on the board of an operator in Turkey, the biggest operator. For the first time last year, actually, our operating cost was mainly driven by the energy. Up until last year, the salaries for the people were the number one for the operating cost, but for the first time, the energy became the main cost. So we need to really reduce the energy consumption, and we are developing mechanisms for that. Again, some of the mechanisms are in software, some of the mechanisms are also associated with the semiconductors. So that's related to 5G Advanced Release 19. What is 6G? What do we expect from 6G? Like I said, nobody knows. It is still a few years away from us. Standardization possibly is going to be starting in 3-4 years. And right now, lots of research groups all around the world are looking at different aspects of 6G. And some of these aspects are, again, one of the things, as Selim mentioned, is integration of non-terrestrial networks to terrestrial networks. So a mix of different networks and how to integrate them together. But there are other things that's also very critical for the 6G. And one thing that many of the presenters mentioned in the morning is integration of AI into the wireless networks, communication networks. There are several reasons for that. Like I said, our networks are not self-organizing. They are not intelligent. So we need to make them more intelligent. So one way of making our networks intelligent, cognitive, adaptive, is utilizing those capabilities of AI and machine learning. Another aspect of integration of AI and machine learning is to generate intelligence from the network, basically native AI. So we design a network that creates intelligence. So this is basically network for the intelligence or intelligence for optimizing network. This integration, either this way or another way, is going to happen in 6G. We already started that in 5G, but I think in 6G, this is going to be really critical. One more thing that we think is going to be introduced in 6G is sensing. Up until now, we had a radar community, and then we had also communication community. But at the end of the day, radar community uses spectrum to transmit a radio signal. Communication community also transmits a radio signal or almost similar spectrum. One is modulated, the other one is unmodulated. Radar signal is modulated in the air by hitting an object and reflecting back. For communication signal, the modulation signal information is transmitted at the transmitter, and after it goes through the channel, it is received. So once we receive, actually we receive two things in the communication. One is the information that's transmitted. The other one is actually the behavior of the environment, because the signal goes through the radio channel, it hits objects, and then the channel or the objects changes the electromagnetic radiation. So at the receiver, actually, we do two things. One is understand the channel, what the channel did to my signal, and then equalize, basically compensate the effect of the channel so that I can demodulate my signal. So far, we never have interest in the channel. We only think that the channel is bad and we have to compensate the effect of the channel. Today, in 6G, we would like to learn something about the channel as well. So that's basically what we mean, integration of sensing and communication. But so far, we never focused on the channel. So our models of the channel were very simplistic models for the better detection of the information. But in the future, in the 6G, we need to have better models, better channel models. We have to understand the channel better so that we can extract as much information as possible about the channel. So this is what I call integration of sensing and communication. At the end of the day, we are going to see a lot of integration in 6G. And all these things brings a lot of difficulties and challenges to us as well. A network, we are imagining a network that will do a lot of things, that will serve for many goals, that will be used for communication, that will be used for sensing, and that will have different behaviors, that will have terrestrial version, non-terrestrial version, underground, under ocean. So we are thinking about different types of network for different applications, for different services, and we need to integrate them all with 6G. So at the end of the day, such a capability from a network requires a very flexible radio access technology platform, and it has to be also adaptive, and it has to have sensing capabilities, it has to have AI and machine learning integration, and the network should learn. The network should have also reasoning, and on the top of all these things, we have to have a very secure network. Today, when we look at 5G, 4G, every network that we are utilizing, the security only comes with protecting information, utilizing crypto-based techniques. We don't protect the communication. We don't protect our pipelines. We only protect the bits, the information. Who protected the communication in the past? Military, because for mission-critical communication, the pipelines are also important. The physical signal was important for military communication because there are so many attacks. Attacks in terms of jamming, attacks in terms of spoofing, attacks in terms of also eavesdropping. And nowadays, in our networks, the number of attacks has increased. So our networks, as much as they became so advanced, so complex, but they became so vulnerable. So we have to come up with techniques, either in the physical layer, we call it physical layer security, or in the upper layers, even in the semiconductor level, to protect the communication, to protect the physical signal, and what we call it physical layer security or secure communication. So this is one of the most critical topics and research area that we are going to see in 6G. So when we combine all these things, then we are going to end up having this cycle, and I call this cognitive cycle. At the end of the day, where we are heading is a network that is so intelligent, that is so flexible, that's so adaptive. We're going to have radios that are also very flexible. We call them software-defined radios, cognitive radios, and all these radios are going to form a network, which we call it cognitive networks. This is not a new topic, actually. We studied cognitive radios and cognitive networks so many years ago, 20 years ago, but it was a hype at that time. Today, it is real. With 5G, it became real, and with 6G, all our communication is going to be intelligent and cognitive. So that's my expectation from 6G, and if you look at all the standards, the evolution of standards, from first generation all the way to fifth generation, it became more and more intelligent, more and more flexible, and more adaptive. So 6G is going to be the extreme version of that. So if I were to define 6G, actually, this is a nice figure that explains what is 6G beyond 5G and compare it with the previous versions. Basically, 6G is the dot that you see on the right. The space that consists of a lot of dots, no picture. Anything before 5G and 6G is the figure on the left. Here, the standard is just connecting the dots. The picture is clear, and there is one picture and one application. But if you see to the right, standard doesn't define anything. Standard only gives you set of options, set of capabilities, and the rest is up to you. And what we call this is network slicing, RAN slicing. I would like to generate multiple pictures from the set of spaces, and I want this set so flexible, so rich, so that I can provide service to anybody, to any application, for any channel condition. So this is where we are going. We want a very flexible world, okay? A flexible world where I can create magics. I can create different pictures, different scenarios, okay? Maybe we won't have any standard after 6G, because after that point, it is just Lego pieces, and then whatever you want to do, just connect these dots, and here you go. You have your own scenario. So that's pretty much, maybe 6G is going to be the latest and the last standard, like our prophet, okay? The last prophet, and then that's the last standard. Now, one challenge that we have, up until now, I always thought that I want a radio that's built on the top of software-defined radio, where minimum hardware and everything can be defined in software. Basically, very flexible hardware. This is my dream world. I have been dreaming about this over the last 30 years. And when we came to this point, my dream didn't happen, okay? I didn't realize this dream. So I came to a point there, we are not going to be able to have a radio that is only defined by a software. Hardware is always going to be there. Why? Again, because of the complexity of the software, it requires processing. It requires analog to digital converter. And when we go to wider and wider bandwidth, the complexity of doing software-defined radio becomes more and more. So it is not making things simpler. Actually, it is making things complex. Yes, it is very flexible, but it is, first of all, more expensive, and it consumes a lot of energy, and also it requires a lot of processing, because again, like much larger bandwidths and very complex networks that we are developing. So this was my dream, but now my new dream is basically integration of analog and digital world. So analog processing for 6G is going to be a very major deal, very big deal. So from a semiconductor perspective, I think we need to think about developing radios in the analog. Actually, the opposite of what we have done so far. We started with analog, with first G, and then we moved to digital slowly. Now we need to go back to mixing of analog and digital. And why? Because analog is low power, less complex, and also, there are many things that we can do in analog domain that we couldn't do in digital domain. What are the applications? There are so many applications, and some of the applications is sensing. Yes, for communication, digital has been better so far. It served us, but it's not communication anymore. 6G is not communication anymore. 6G is more than that. So 6G is integration of many things. So if you are integrating all these beautiful things, you also have to integrate digital and analog together. So wake-up radio is one example that I gave you. We need to have a radio very next to our main radio, and that radio should definitely be analog, even though, again, we are discussing about digital version as well. And beam backscatter communication as well. So the long story short, 6G brings a lot of opportunities for us. 6G integrates many things together. 6G is going to be a very flexible standard, and which will allow us to create so many slices for the applications of today and possibly the applications of the future as well. And 6G should integrate analog and digital world together. Thank you.
Hello, everyone. With this presentation, we end up the session for the path to 6G and beyond. I would like to thank all the distinguished speakers that joined us. And also, just to end up, also this will make the end of the day. And hopefully you enjoyed the presentation for the day. And we are looking to see you tomorrow for another interesting day. Thanks, everybody.